Good morning, everyone, and welcome to the second lecture of algorithms and data structures. I always provide a quick summary of the previous session at the beginning of a lecture, and then we'll continue with the content. If you have any questions on last week's lecture, always just send it in the chat or raise your hand here in Zoom, and I'll be happy to answer your questions. In the first lecture, we discussed why this course is actually relevant, because for somewhat sophisticated software, you need not just coding, but you need an understanding of algorithms and data structures and how to store and work on data efficiently. In order to do algorithms and data structures well, you also need a good understanding of mathematics. And we've looked at some definitions, what an algorithm is. And we saw examples of algorithms. We are surrounded by algorithms, and we looked at a classification of algorithms that you should definitely bear in mind. We saw a data structure allows us to organize and access data, and with algorithms, we work on data structures. We've seen example data structures that we deal with and everyday examples of algorithms. This course is tough, and you will need that understanding of algorithms and data structures probably until the end of your career. And we've also discussed that ChatGPT maybe works very well on those standard algorithms from the literature from an introductory course, because ChatGPT has been trained on a lot of sample data. But once you apply these tools to real-world algorithms that you would develop in industry, they still work, but probably to a smaller extent. So in order to build more advanced algorithms, you need an understanding of the foundation algorithms, as well as the data structures. We saw the organization of this course and some of the literature I recommend, in particular, the book on the left, written by Goodrich and his co-authors. And we also had an intro to Python last week, so that we're all familiar with Python. And we started looking into graphs, which are a foundation data structure, and all the other data structures we look at in this course. They are just some kind of graph with certain variations. We looked at a definition of a graph, and we said a graph is a tuple, and in this tuple we have two sets. One is the set of vertices, and one is the set of edges. And in this initial definition, we worked with undirected graphs that did not permit loops. Something like this here is an example. And then we worked with increasingly more complex graphs. We looked at adjacency matrices, which are just a different representation. And we looked at undirected graphs that permit loops. And we looked at directed graphs and directed graphs permitting loops. Today, we will look at a last graph definition. And for this, I will also switch back to my whiteboard. And once we have done that, we will be looking at a few examples of how you deal with graphs every day. And after that, we will start working on a couple of graph algorithms. And then we have a great foundation for the remaining course, because most of the time we'll be working with some kind of graph algorithms. I'm sharing now my iPad, and today we want to extend our framework, because so far we have worked with directed graphs, but now we want weighted graphs. So we want them weighted. And what that means is, if we have a graph with various vertices or nodes, we've seen before how we can define them in a directed way. And for example, 1 and 2 are connected in both directions, but 2 and 3 are only connected from 2 to 3. And 4 and 3 are also connected in both directions. All of this is something we can describe already with our framework we did last week. But now we're going to add something. We're going to add weights to these connections, because before we assumed if we say going from one node to the other is a cost, that all these costs were the same. But we can vary this now. So we can say going from 2 to 3 costs 4. For example, this graph could represent distances between cities, and 4 is a certain distance, like maybe 4 kilometers. Going from 2 to 1 costs 2, while going from 1 to 2 costs 3. Maybe they're just roads in one direction, and it just takes you a little longer to drive the one road than if you return. From 4 to 3, it costs 2, and from 3 to 4, it costs 1. So this is a weighted graph, and if we take our framework from before, we can try to extend it. Before we said a graph is a 2-tuple, but now it's actually a 3-tuple, because we have the vertices and the edges, and we also have a distance function. V and E is as before, but I'll just write it down as a revision. V is the set of vertices, exactly as we handled this before. E is a subset of the Cartesian product of V with itself. We've seen this last week as well. And now we introduce D, and D is a function that maps from an edge to some real number. And the definition is also written in the slides with a little bit more text for your revision. So D is a distance function. And we can try to do this now for our sample graph. We can say, well, our sample graph here is a 3-tuple V, E, and D. And for your revision, what I want you to write in the chat, what is V? So that's just a revision of what we did last week. And then once I see your answers in the chat, what V is, we'll continue with E. And then we will also define the distance function. So if you have a suggestion for what's V, send it to the chat, please. And we got the right answer already. It's a set of 1, 2, 3, 4. If you have a suggestion, what's E, please send it to the chat. E are only the directed edges. In E, we write nothing about the weights. So ignore the weights when you write E. But if you have a suggestion for what's E, send it to the chat, please. And I'll do at the end a definition of D, which has to do with the distance, in order to show you what that is about. And I'll wait for your answer or your suggestion what E could look like. We got first suggestion in the chat. 1 and 2 are directed connected. Then 2 and 1. So remember, these are directions, so it's tuples. Then we have 2 and 3 connected, 3 and 4, and 4 and 3. And what we got in the chat from a couple of you looks okay. Now we also need to reflect somehow our distance function. And I'll do this in red because it's a new part, and maybe also up here, I'll write it in red. We're all just on the same page. So D is a function. D of E, we pass an edge, and then it's a piecewise defined function. We can say that the weight is 3 when E is the tuple from 1 to 2. This I'm just marking it in blue would be this connection here. It's 3 when E is the tuple 1, 2. The connection or the weight is 2 for E that is 2, 1. That's the next one I'm highlighting in blue. Then it's 4 when E is 2, 3. The connection from 2 to 3. It's 1 when E is the connection from 3 to 4. And it's 2 when the connection is from 4 to 3. So this is one way how you could define this function. It's a piecewise defined function. And overall, you could also write it in a shorter way because we have a 2 in we have a 2 twice here and there. So you could update this if E is the one thing or the other thing. Then it becomes a little bit shorter. So this is our piecewise defined function. And we also saw last week the concept of an adjacency matrix. And we can also be thinking now about an adjacency matrix in order to represent this. I'll just want us to have enough space. So I'm just going to remove this definition from here, but you find it in the slides anyway. So just tidy it up because I want to be able to write it next to the graph, so we can be looking at the adjacency matrix. And the adjacency matrix for this graph is a 4 times 4 matrix. So I'll write this here, the adjacency matrix. And what I see is there are no loops in it. Our definition allowed loops, but we didn't take advantage of any loops so far. So I see the diagonal are all zeros because there are no loops in it. And then I see going from 1 to 2 costs 3. So I make the assumption that the row means from and the column means to, but you could also just transpose the matrix if you see it vice versa. But going from 1 to 2 costs 3. So this is this 3 here. And that's the only connection that is outgoing from 1. So the others are all 0. Going from 2 to 1 costs 2, which is what I'm also now again highlighting blue. It's this one, but we can also go from 2 to 3, which costs 4. And that's it. We cannot go from 2 to 4. And I want you to write in the chat what the next row of the adjacency matrix is, meaning the outgoing connections from node 3. If you have any suggestions, send this to the chat. Just the next row, please. I got the right answer. It's all zeros except the last element. And the last element is going from 3 to 4, which is just this 1. So that's why 0, 0, 0, 1. And then the last row is just the one from 4 to 3, which costs 2. So that's the 2 here, and there are no other outgoing nodes. We can also try to amend this. For example, in green, we could put in a loop in 3, and the loop costs 9, for example, and we could just amend this. And loops are always in the diagonal of the adjacency matrix, and then we could put in the 9 here. Our definition from before also allowed loops. Maybe just give me a signal with a green sticker if you're okay with this example, or a red one if there are any doubts. And if there are any doubts, please let me know. in the chat or turn on your microphone, and I'll be happy to see how I can help. With there only being positive responses, I assume you're okay with this. So this was our example of weighted graphs that permit loops, and the definition is written neatly in the slides. And I'll switch back to my slides now. So this is the definition we discussed just a moment ago, and that's the example that we discussed. You also see the adjacency matrix. And now you're probably wondering, what are graphs useful for? So graphs are a very generic data structure, and if you look at other data structures from this course, like lists, trees, and so forth, those are just variations of graphs with certain constraints. So we'll be dealing with some sort of graphs, most of this course actually. There are all sorts of graphs algorithms that are essential to computer science. For example, routing, if you interpret the nodes as cities and the weights as a distance, you can figure out the fastest route going from one to the other city. These two algorithms that we're discussing in this course are shortest path and lowest cost. We'll be discussing them very soon today. You can also ask yourself a different question. You have a list of cities and you want to visit each city and return, or you want to visit each city once and you want to return to the original city where you come from. This is something that is called a traveling salesperson problem, sometimes the traveling salesman problem. No, it is typically probably a salesperson problem. That's a graph algorithm. You can also be thinking about dependency resolution. Imagine you want to load packages in your Python environment, and you have to load one package, but it depends on other packages. So you need to figure out which one to load first. And then the next one, because maybe in order to load a more advanced one, it relies on others that need to be loaded first. And that's a dependency resolution. And in a graph, you would represent dependencies in a directed way and say that this package depends on another package. And in fact, there's an algorithm for you already at hand. It's the topological sorting. And topological sorting can be used for dependency resolution, but also for other problems. Maybe in computer graphics, you have a polygon, and you want to know if a point lies inside a polygon or not. This can be important, for example, when you determine when you shoot, if you hit a target or not, but can also be used for other problems in computer graphics. So this is the so-called point in polygon problem, can also be referred to as a graph problem. And all of you are dealing with graphs and graph algorithms all day long. For example, if you use social networks, they are graphs because you have friends and your friends have friends. So it's a big graph. And in there, maybe you want to recommend potential friends. Maybe you want to find a clique. A clique in graph theory means that you have, in a clique, all the nodes are connected to each other. So you could also refer this to maybe your inner friend circle where all of you are close friends. So that could be a clique. There are algorithms to find your cliques in graphs, and this could be applied to social networks. But also a neural network is eventually just a graph with certain properties in it and various constraints. So maybe you want to train a neural network, and that is eventually an algorithm we call backpropagation combined with, for example, gradient descent. But eventually, you could also say it's just some special graph algorithm. If you have a knowledge graph where you interconnect knowledge, you may want to make some inference in there about knowledge. Again, it's some kind of graph problem. Or a distributed ledger, such as a blockchain, is eventually also just a graph with some extra features. Maybe you want to manage some data in your distributed ledger. So graphs are important to all of you. In this course, we have students studying AI, so you would be dealing a lot with neural networks, graph mining, knowledge graphs. So you'll be dealing with graphs all the time. But those of you who are studying cybersecurity, who also take this course, maybe some of you are interested in distributed ledgers, such as blockchains, which are also some kind of graph eventually. So graphs are all over the place. And we could do the whole term only graph algorithms like topological sorting, traveling salesperson, and so forth. And sometimes in some departments, there are lectures only on graph theory, but we don't have time for this in this introductory course. So what we are doing is we're looking at two algorithms, which are called shortest path and lowest cost today. And then we have actually built a good foundation for this course because you know about graphs, you have seen some graph algorithms, and from there we will look into more specialized graphs like lists and trees. Those are essential data structures in computer science, and we see how to work with them and how to work with them efficiently. Maybe you can indicate to me if you're new to Python. If you're new to Python, maybe green sticker. If you have used Python before, maybe a red sticker, because last week I provided you with an introduction to Python. However, most of you have probably dealt with Python, but there are always some students from a different degree program or exchange students or whatever who have maybe not had that exposure to Python yet. However, I only see responses from you that mean you have dealt with Python, because we'll today be using a few more features in Python in order to build our shortest path algorithm. The shortest path algorithm is a graph algorithm. It's a search algorithm that finds the shortest path from a start state to a goal state. And we're defining this algorithm in a somewhat more generic way than maybe you would do it in most other classes, because when you look at the shortest path algorithm in a typical introduction course to algorithms and data structures or to graphs, this will often be just treated purely from a routing perspective, where you want to go from one city to another one and find the most or the shortest path or the best route. And there are algorithms for this, like the Dijkstra algorithm. But in this course, I want to do something that is a little bit more generic. We'll be thinking about states in general, and a state could be just a single node that is, for example, a city and you have a distance. But we'll be looking at that from a much more generic perspective, because you could have different actions, so not just one weight going from one state to another, but there are different actions you can take. And these actions will also come with costs. That's something with different actions that we will do later in the lowest cost algorithm. We're starting with a simplification of this with the shortest path, and later we will extend this to different actions. And we're not caring too much about routing. Routing can be an application of our framework, but we're dealing with highly generic states, and we're building a highly generic search algorithm. And we are thinking in a very abstract way of this. We say we don't care really what's in the node. We only care that we have states, and we can go from one state to another or not. And we want to find the shortest path going along these states from our start to our goal. We only care about hops, meaning a hop is going from one state to another. So far, there are no weights in there yet. Weights will come later in our lowest cost algorithm, but in shortest path, we just want to keep the number of hops the lowest. And we can also then say or define the successors of a state. And eventually, when we look into a state, we look at its successors, and we try to find an efficient route from the start state to the goal state. We will be soon developing or coding the algorithm, so that I'll show you live how to code it. And we will build a function that is called shortest path, and it will have 3 parameters. One parameter will be the start, and that's the start state. And we will then pass references to two functions. One reference is to the isGoal function, and the isGoal function will return us for a specific state, whether the state is a goal or not. And the successors function, to that one, we can also pass another or a state, and it will return its successors. So where you can go to from one state. I'll briefly show you the concept on the iPad, and then we'll be coding it. And we need also a very fundamental concept for in our search algorithms that we call a frontier. A frontier contains the so-called non-visited successors of previously visited states. Initially, we just put a start state in the frontier, and we have explored the start state then, so we don't want to go there again. So we put it in a different list of the so-called visited states. But we put the successors of the start state into the frontier. We could also abort if the start state is our goal state. That could also happen, and we're just done. But if we're not done with that yet, we put all the successors of the start state into the frontier, but only the ones that we have not visited yet. Because later you will then pick something from the frontier, and we will pick something from the frontier, explore its successor states, but if we have already visited some of these successor states before, we will not be visiting them again. So the frontier will only contain all the non-visited successors of previously visited states. And for our first algorithm, the shortest path, the frontier is sorted by the path length in an ascending order, meaning we will look at the successors with the lowest number of hops, and then if there are more states we have added to the frontier, we always add at the end. So always the ones that take more hops, they come at the end of the frontier. I know it's still generic, but we'll be looking at examples and we'll be seeing how we can code that. And the frontier is a fundamental data structure that we need in our algorithm. I will now briefly describe what we want to do on the whiteboard, just as one example that you can get a little bit of an idea what we are planning to do. So we're going to work with the shortest path algorithm. And we will start with a start state, for example, state 1. And we are putting that one in the frontier initially, because that's the start state. We would also check initially if the start state is our goal state, but if that's not the case, we continue working with it. And our start state has multiple successors. For example, 2 successors, 2 and 3. We would then generate these successors, and we would add the successors at the end of the frontier. So we could try to explain this step by step. So initially, we put in the frontier our state 1. But we look at state 1, and state 1 does not contain or is not our goal state. So we will, in the next step, or we will first remove the, so we say frontier is a list. We will remove that state from our frontier because it's not our goal state. And then we put the successors of state 1 in our frontier, which are 2 and 3. But we only put them in if we have not explored them before, because we will also have a second or another data structure, which we call explored. And in explored, this can be a list or a set, whatever. We are storing which nodes we have already stored, or which ones we have explored so far, because we don't want to be exploring them again. 1 is explored, and 2 and 3 are successors of 1. And then we say, well, let's go to state 2 now, because it's the leftmost element in the frontier. So we would be removing it. And so far, we only have like 3 in the frontier left. 2, we can check if it's our goal state. We say it's not the goal yet in this example, but say 2 has multiple successors. For example, we have our successors 4, but 2 would also have a successor that is 1. And then we would update our frontier, which contains 3 so far, which has not been explored, and 2 has the successors 1 and 4, but we only put 4 into the frontier now because 1 has already been explored and we don't want to explore it again. Now we have put 4 into the frontier, but we're not done yet. And then we go to the frontier and we take the first element from the frontier, which is 3. So we remove it from the frontier. And we can say, well, in our example, 4 is the goal. 3 is the goal. And then we are done. We have found our goal. And eventually, our frontier, which you will see soon in the example, stores a little bit more. The frontier not always just stores the individual states, but actually the whole path, how to get to that state. But that's just simplified for now. And then we know, well, we have found 3, and if we store the whole path in the frontier, we can say, well, going from 1 to 3, we have found our goal. This is now an extremely simplified example, but I just wanted you to see the concept of the frontier and explored. And we have to add one more thing to actually explored, because we had explored also 2 and removed. So we removed it from the frontier, we explored it, we put it in explored. Because with the explored list or set, we just want to make sure that we are not going to states again that we had already explored. And this is now a very simplified example. We'll be coding the generic algorithm very soon. What you need to bear in mind, the states we are working with now, they are far more complex, because they may not just contain a single entry in their node, they could contain multiple values or other objects. So we're building this in a highly generic way, and we don't really care what's in the states, but we only care what their successors are and what the goal is and how to get efficiently from the start to the goal, or maybe even abort if there's no goal. If we don't find the goal at all, that could also be happening. But it's not just numbers that we put in, but it could be totally different objects. And after we code this, we'll also be looking at a concrete example and how to run it. And then you'll see what's the beauty of this generic approach. So this is the example of the shortest path algorithm. And I'll be coding this with you now, and you will see how it works in detail, because I think coding this from scratch will certainly make it easier for you to understand. I want to know from you beforehand, who of you is familiar with references to functions in Python? So you deal with functions, but you can also pass references to functions. If you're okay with that, if you know how it works, so how to deal with function references, maybe send me a thumbs up. If you don't know this or you would like a revision, maybe send a red sticker or a thumbs down, and then I'll briefly provide a revision of function references. So there are only red stickers, so those of you who have done Python before had not seen that, but it's fine. We will do a quick test or a quick demo of how this works beforehand, because we will need these function references very soon. We can say we have a function f1, and f1 has a parameter that I call p, and f1 just returns 2 times p. It's just an extremely simple example. And then I have a function that I call outer. And the outer function gets a parameter, but this is a reference to a function. And what it will do is it will call the function reference, or the function to which the reference refers, and we pass the value 10, and we want to print this. So if I call outer, and I call outer on a value 2, like value 2, for example, it will return an error, because it doesn't work that way. Because what I need to pass is not an integer, but a reference to a function. And in the outer function, we will call this function to which we have the reference, and we pass value 10, and then print what that function returns. So we can call outer and pass a reference to f1. You're not calling f1, you're only passing a reference to f1. And then we're passing the reference, and then the outer function calls that function to which we refer, passes the value 10, and we had passed f1, and f1 returns 2 times p. We could also define a different function, f2, which returns like 5 times p, and we can also call outer on f2, and then we would get 50. So this is a very simple way how I can pass a reference to a function. And you can also do this, for example, in C or C++ with a pointer to a function. Last week, some of you said they had done C, C++ before. If anyone has ever worked with a pointer to a function, maybe just let me know this here in the chat if you have ever done this. Maybe just send a yes or something, and then I see if anyone has done this. It's something you can do in Java, but it's much more difficult to do this in Java, and Java is not really made for that. So maybe something you would hardly see in Java, but in Python you can do this. We can also look at the type of f1, and we see the type of f1 is a function, and so is f2. And what I'm passing is just a reference to f1 and f2. You can also look what f1 refers to. We see it's a reference to a function, same with f2. And I'm passing this to the outer function, and then it's being called. If you're okay with the concept of a function reference, maybe just signal me this with a positive sticker. If you have any doubts about function references, please let me know. And so far, I only see positive responses. So this was a quick intro to function references. And now we'll actually start coding our shortest path search. And we'll be doing more or less than like what I had shown you on the iPad. But there are a few more special cases we need to be looking at. The algorithm that I'm showing you is also in the slides. But I feel if we code it together live, it will certainly be more helpful. And I hopefully don't have a lot of typos, and it will actually work in the first go. We are passing a start state. A state from now on could, for example, always be a list, or it could be a tuple, or we'll see what these states will look like exactly later in a concrete example. But it doesn't matter for us what's exactly in a state, because we get a reference to the successors function and the isGoal function. And they need to be coded accordingly to the exact search problem. Later, we'll be looking at concrete search problems. It could be routing. So maybe start is just a city, and the successors function would return us for a specific state what the cities are that city is connected to via its roads. And the isGoal is also a function reference, and the isGoal function would return us for a state, whether that state is the goal state I'm looking for or not. But within my generic search algorithm, I don't care about the exact structure or content of my states. I only care that there are states, and that the successors function and the isGoal function know how to handle those kind of states. So they need to be implemented for that according for that specific search problem. But we are solving now the search problem in a generic way that we only deal with states and we call these functions and we do all the management around that. And then for your specific problem, you need to implement your functions. But you don't need to think about the actual search anymore. So we could first check if the start state is actually our goal. If that's what I want, then I'm done. So isGoal is a function, and I have passed the function reference. So I can call this function. And if this one here is the start, then I'm done. So I could just return start. However, our shortest path search will always return a list because it will later return a set or a list of which represents the whole path, because you go from the start state to a next state to a next state until you are in the goal state. So we always want to return a list. If we just return a single element, we just put it in a list and then we're done. Later, the lists we're returning, they are more complex because they will actually be a whole path, and paths are the next thing we'll be working with. We also need our frontier, and the frontier is a list, and it will contain the start state, but it will be a little bit more complex now because we're not just putting in the start state in the frontier. Before, when I briefly explained that concept, I said the frontier will always contain paths. So how to get from the start state to the next state to the next state. So we're actually also storing lists in the frontier because the frontier contains the start state, but the start state will later be part of a bigger path, and paths are always lists. So we're just putting this list with a single element, and the frontier itself is a list because it will later contain multiple paths. So we have a list of a list right now. It's just to get started and to avoid that we have special cases if we don't have a list in it, but just a single state. So we're always storing paths in there, and the initial path is just a single element. That's why we put a list into this list. I also need to keep track of my explored ones, and the explored one is actually a set. You all know the difference between a set and a list. A set is unordered, and we can search more efficiently in this unordered set. And this is also natively implemented in Python as a data structure. And what I actually just want is a set of this list start. So the list contains start, and I'm turning it into a set. And later I can just check which nodes or which states are in the set, and I can add more. So it looks a little bit cryptic, but all I'm doing is I want a set in which I put in the start element. Now I have built my essential data structures, and what I want to do is I want to take the first element from the frontier. What I can do is I can do frontier pop of 0, because frontier is a list, and these Python lists, they offer a pop method. And pop 0 means give me the leftmost element and remove it from the list. So it will return me something, and what it will return me in the first go is actually just this list within the frontier list. So pop 0 means give me the leftmost one, and if there's only one in, it's the leftmost. It's being removed and returned, and I store it in path because I will always be dealing with paths, because this is now a list that I have here, and it's just a list with start. When we discuss lists in a couple of weeks, you may see that doing a pop 0 is not the most efficient way how to do this, and maybe we could represent a frontier with a different data structure, not with a list. But that's something we'll be seeing in a few weeks when we actually discuss lists and other data structures. It's quite an inefficient way to do this with a pop 0, but for now it doesn't matter. We don't care too much about efficiency yet, because for this we need our complexity framework, which we will start discussing later today. Then, actually, I don't just want to pop once. Actually, oops, sorry, I clicked the return too early. So I'm starting again. Actually, what I want to check is, as long as there is still something in the frontier, I want to be doing that, because later or before I said, we always take from the frontier as long as we have not reached our goal yet. So I check while frontier. This means this while loop runs as long as there's still something in frontier. If you try to code this in Java, it's a little bit more code, because you would check while the size of the frontier is greater than 0. But in Python, you can just write while frontier, meaning this loop runs while there is still something in the frontier. Then I'm taking my leftmost path, so the next element to take from the frontier. And this path is when we are starting, it's just a list in which there is the start state in, but later it contains multiple states in that list, because it's a path going from the start state to some state, then to some state, and so forth. That's why I want to take the rightmost element, so the last state in my path. And we had seen this last week when we looked into the introduction to Python. If I pass the index -1, it gives me the rightmost element in the list, so the one that was added at the end. And I want this one because this is the rightmost one is the last state in my path so far. When I start with this initial case, it's actually just a single element, so it just gives me the single element, but later these paths will be longer. Now, what I want to do is, I want to call the successors function. So successors for some state, and S is that state we're now investigating, because it's actually that state from the frontier I want to look at. Because remember, the frontier contains more than states, it contains paths, but this is the last or the newest state in the in the path that I want to explore. So I want to get its successors. Now you're wondering, how does this successors function work? We will later define a concrete successors function, and we will see that the successors function works with dictionaries in Python. Last week in the intro to Python, we looked into dictionaries, and we saw a dictionary contains key value pairs. And with the so-called items function in Python, you will get all key value pairs from a dictionary. So we're assuming the successors function returns a dictionary, and with .items, I get all key value pairs. And I want to go through that, and concretely, these key value pairs that I'm getting, which are always two elements, the left one is the state, that's actually the key, and the value is the action. So the dictionary, I can pass a key and say, for that key, I get that action. And the action would actually be where I'm going to. And I have a loop because my state S that I'm investigating may have multiple successors. And later, when I'm coding the successors function, I'm simply assuming that it returns a dictionary. And we'll be seeing how we can write such dictionaries. Then I have to check, I'm going through all these successor states now of S. I need to check if the state is not in explored, because I don't want to look at states that I have previously explored. And with not in, I can just check if a state is not in the set, and this set will later be growing. If it's not explored yet, I say, well, now I'm exploring it. And so I'm adding this to explored, because now I'm exploring the successors, or that successor, so I don't want to explore it later again. Now I'm creating a new path, which is just the old path, and I am actually adding this list. And just for clarification, I hope I explained it before. Actually, I think I made a small inaccuracy when I explained this. What the successors function gives me are the successor states and the action how to get there. So now it's correct. Because successors of S in the dictionary, I have the successor state and the action how to get there, but it will be more clear later when we're coding a concrete example. So I take my old path and I'm adding a list. So the list now is which action and which state are following. And this is the new updated path. I'm checking if that new state that I'm looking to in the successor is actually a goal. And if that's the case, I'm returning that new path because it's the old path plus an action and then a state. And then I'm done. If this new successor I'm looking at is not a goal, I am adding this new path to my frontier, and appending means I add it at the right end. Then I'm almost done because now I've added something to the frontier and this loop keeps running. The outer loop keeps running. Once I have explored all these successors and none of them is a goal, then the frontier picks the next element from the frontier and the loop keeps running until I'm done. So this loop would keep running until I find a goal. However, if at some point the frontier is empty, and empty means none of these successors eventually led to a goal, and also for the other elements in the frontier, and I run out of elements in the frontier, then the frontier is empty because I have no new successors to append, then I have failed. So I can just return an empty list, and an empty list means there's no path going from the start to the goal. And I guess this looks highly generic for you. This highly generic approach has a lot of benefits because I'm not really caring what these states look like. The states could be cities. They could be far more complex things, far more complex state objects that I'm investigating. And simply I get from one state to the other by taking some actions. We're actually handling multiple actions here. We are not handling costs. Costs could be that a different action has a different weight. This is something we'll be seeing in the lowest cost algorithm. And we will be now looking at a concrete example. And this concrete example is also in my slides. The shortest path algorithm that we have coded is just here. And I hope I didn't miss anything, and I hope I don't have any typos in it. We'll be seeing later when we run it. But the correct implementation is in here. You don't need to copy paste from the PDF slides because copy pasting from a PDF typically leads to all sorts of issues. If you take a look in the Nextcloud directory, there is a zip file in this course folder. And in the zip file, there are plenty of code examples that we're coding in this course. And you can just copy paste from those Python files, or you code it on your own. But please don't copy paste from the slides because this typically only leads to problems that will be very hard for you to fix. Now we are looking at the pouring problem. And the pouring problem is one application or one example we're now investigating, and we will see what the shortest path search is useful for. In this pouring problem, you need to imagine you have two classes, and these two classes have a different capacity. I think I can also visualize this on the iPad, and it will be more clear. So we'll be looking at the pouring problem. And in the pouring problem, we will have two classes. We will have classes of different capacity. For example, the left class has a capacity of 418, for example, milliliters, and the right class has a capacity of 986. And we are starting with both classes empty. So they're both empty. And we only have a certain number of legal actions we can do. Legal actions can be, we can totally fill a class, or we can totally empty a class. So we could totally fill the left class, or we totally fill the right class, or we empty each of them. So these are four possible actions we can take. But we can also pour the content of one class into the other class. And pouring means we pour all the content from one class into the other, but we're not allowed to pour over. That means if we have in the right class 500, we cannot just pour like maybe 200 into the left class. We can only fully pour it in, but we cannot just keep pulling or pouring over so that some water flows out. We are not allowed to do this. And I'm obviously not allowed to take maybe just 10 milliliters and pour them from the left class into the right class and so forth. So that's not a legal action. And I have a goal. So I'm starting with 0, 0. And the goal is, with these actions I'm allowed to do, that I eventually get to a state where I have 6 milliliters in the left class and 0 milliliters in the right class. And I'm only allowed to take these actions, fully fill a class to its entirety, empty a class, or pour from one class to the other. And I want to get from 0, 0 to 6, 0. And I want to know the shortest number of actions I need to take in order to get from 0, 0 to 6, 0. And obviously, I'm not allowed to just fill the left class initially with 6 milliliters. I can only fully fill it or empty it or pour from one class to the other. And it turns out that the shortest solution is 618 actions. Maybe right, actions, in order to solve this pouring problem. If you try this now at home with two classes, probably you will never finish finding the shortest solution, and it's 618 actions. And you're wondering, how can you solve this? And it turns out with our highly generic state search, we can solve this because we've only assumed states. States could be cities. A state could also be the filling of two classes. It could be lots of other things. We could have some graph, whatever, or some totally other optimization problem. And here our states are just two classes that have a filling. And I have these actions, fully fill a class, fully empty, or pour from one class into the other. And I want to get from 0, 0 to 6, 0. I take 618 actions. And we'll be investigating now how to solve this with our algorithm that we have just built. We will now briefly come to the coursework document, because last week I talked about the coursework and I said there's a mandatory problem, there's an exam bonus problem, all the other problems are up to you. If you're new to Python, you should do the Python primer. Has any of you worked on this Python primer so far? If you have, maybe thumbs up or thumbs down if you have not. It's just some practice for Python. And remember, if there's an R or P or C, this always refers to the Goodrich book. And you can access the Goodrich book for free through our library as an ebook. So there are a few Python primers just to get comfortable with Python. And today we'll be looking at section 7, which are graphs, and there is problem 7.1. And 7.1 is just a pouring problem that I had mentioned. And we'll be solving this now together. So it's one coursework problem we are doing together. So you just become more comfortable with the shortest path search. In order for you to solve this, I have already put in quite some code that you're okay with the shortest path search. I will just recode this now and explain it for you. And we actually just need to fill in a few elements, and then we are done. Very easy. With the successors function, we need to be thinking about the isGoal function, and we're calling the shortest path search we had just coded. I will switch back to my coding environment in order to write this with you. We want to call our shortest path search. So we're calling shortest path search. We need to put in a start state. We need to write a successors function and the isGoal. But we can only call it once we have written our successors function and the isGoal function. We are starting with the isGoal function. So the isGoal function gets a state, and we are returning whether that state is 6, 0. So in our example, I'm just assuming that a state here with that we're working with is just a tuple with 6, 0. So 6 is the left class, and 0 is the right class. And I also need a start state, and the start state is 0, 0, and I want to get from 0, 0 to 6, 0. So I already have two elements I can pass to shortest path, the start as well as the isGoal function reference. The tricky part is now writing the successors function, and we will try this together. The successors function is a little bit more complex. We will define successors, x, y, and x, y are actually, later when we call it, the capacities of the left and right class. So not the filling state, but the capacities of how large these two classes can be. And I want to know from you, who of you has, since most of you claimed you have done Python before, has anyone ever put a function within a function in Python? If you have done this, maybe thumbs up or some red reaction, or thumbs down if you have never put a function within a function in Python. So there seem only to be students who have not done this. The good answer is this is something you can do fairly easy in Python, and I'll show you why. In Python, you can just put functions within functions. It's something you can do in some other programming languages, but you cannot do it in Python. The outer function is called successors, and in here, I will define the capacities of the left and right class. The left class in our example, we said it's 418. The right class is 986 or something like that. And I want to be able to work with these capacities in my actual successors function. And the actual successors function our algorithm will be dealing with is an inner function. And what I'm doing here is, later, when I call successors, I pass these capacities of the left and right class, and then I'm actually returning a reference to an inner function. And this inner function is the actual successors function the algorithm will be working with, but somewhere I need to be storing these capacities, and I don't want to store them outside in a global variable or something like this. So what I'm doing here is I'm just calling successors once with these capacities, and I'm returning a reference to the actual successors function, which is the inner function, but it can use those as parameters within the inner function, but they're not global parameters somewhere in the global space of the program. So I'm just returning in here a reference to the inner function, and the inner function can use these parameters very easy. So this is no magic. The beauty in Python is I can simply put functions within functions, and everything is an object. Now, the inner function, this SC function, will later be the one I'm passing to the shortest path search. And what we've seen is the successors function is called only once in our algorithm for a state S. So I'm passing a state, and the states in my, or I don't care in the shortest path search what a state looks like. I only care that it's a state. What the state looks exactly, I need to worry about in the isGoal function when I define the start state, or in the successors function. And what I know is it's just a tuple of a left and a right filling of the classes, and the tuple is called state, and I can break up the tuple very easy in Python because I introduced two variables, x and y, in lowercase, which are the fillings of these two classes, and I'm breaking this tuple into two elements, which only works if this is a tuple with two elements. If it's something else, this will lead to an error. But here in my controlled environment, I'm just assuming that. And just to make sure that there's no strange error or inconsistency in our program, I can also put in an assert. Who of you has ever worked with an assert? Maybe give me some reaction, whether you know what an assert is or not. Also exists in other programming languages. Some of you have used this. So an assert is just a check if this condition holds true. So, and if it doesn't hold true, the program will abort with an assertion error. And here, this is just a quality check. I'm checking that my capacity X is a valid, sorry, not the capacity, that the filling of the class is valid, because the filling needs to be less than or equal to the capacity for the left and for the right class. Ideally, I could also check that I don't have negative values in here, but for now, we just put in this assert. And in case we make any strange mistake when writing our successors function, such an assert can always be helpful. The program will terminate at the right moment, and we can revise our code and see if there's any problems in it. Now, I need to return a dictionary. And this dictionary is, so I call this, for example, result. It's a dictionary, and I'm going to return this result. And now I'm slowly building this dictionary. And remember, the dictionary has a key, which is a state. That's the successor state. And the value is the action. So which action I'm actually taking in order to get to that successor state. So I need to add key value pairs to this. And what I can say is, well, one key could be, for example, or we'll be typing this, and the actions in this example are just strings. So it's a visual or it's something we can actually read out later. So the action is a string, and I say I want to fill X. So I want to fill the left class to its entirety. What I don't do is I don't touch the right class. The right class has value Y, and I'm just keeping it to Y. And the left class I'm filling to its entirety. So I'm putting in the capital X, which is the capacity of the left class. So I've put in one action. Now I want to know from you, which action do I need to put in, or which state do I need to put in for the action fill the right class, fill Y? What do I need to put here in this tuple? If you have a suggestion, maybe turn on your microphone or send it in the chat. What do I need to put in here as the state in order to fill the right class? Got the right answer. Small x, lowercase x, because I don't touch the left class. I only touch the right class and I fill it. Then another action can be, I am emptying X. What do I need to do as a tuple in order to empty the left class, not touching the right class? If you know this, send this to the chat. What you would do just to empty the left class and not touching the right class. We got the right answer. It's 0y, because this means the left class is just 0 and the right class is not touched. And if I want to empty the right class, it's just x0, and I am emptying the right class. So these are 4 actions I have implemented here right now. And there are actually 2 actions left, and they are a little bit more complex. And I will show you them now. And they are actually, or I'm typing this as a comment, I need to pour from the right to the left class. This is one action I need to take. And one action is I'm pouring from the right to the left class. I will now refactor and rewrite my code a little bit, and then it will also look like what it looks like in the course worksheet, because in the course worksheet, we have defined this dictionary in a slightly different way, and it will actually look a little bit neater, and we actually need a little bit less code, because I have defined here a dictionary and I'm filling it and I'm returning it, but rather I want to return a dictionary directly. And we are doing this now. And these ones here, I will just remove them in a moment, because in Python, you can also say, I am returning a dictionary, and the dictionary you use to open and close these curly braces. And here, I can put in directly the key and the value. So the key would be a tuple where I'm saying my x, y to fill. Then I have the ones, I'm just copying them from before. One is the fill y. We have the 0y, which is the empty the left one. And this one here was emptying the right one. So we've just, before we had manually composed the dictionary element by element. Now I'm just returning a dictionary that is built directly this way. So it's doing exactly what I wanted to do. But I still need to look at these 2 actions, move from right to left and from left to right. And we are starting with pouring from X to Y. So I need something here as a key, and as the value, I'm moving from X to Y. Probably coding this left one is a little bit tricky, and I'll show you now why. And then you'll also see why I've moved to, or why I've refactored to return this dictionary directly, because it will be a whole lot more easy to read. What I'm doing now is still a little bit more tricky to read. You will see this in a moment, but it's overall not that difficult as it first seems. So I want to move everything from the left to the right class. That means if I move from the left to the right class, the left class will be empty. So I will have a 0 here. And in the right class, I have a y plus x, because I'm taking what was in the right class and I'm adding x on top. Can this always work? I'm asking you, what could, does this always work or not? If you have a suggestion, let me know, maybe turn on your microphone or write in the chat if I can always just pour everything from left to right, and what could maybe go wrong. If you think this can always work, maybe green sticker or red sticker, we don't, but we got an answer now from a student who says no, because maybe the right class is full at some point. So this wouldn't work. So I can only do this if y and x are less than or is less than or equal to the capacity of the right class, because otherwise I'm unable to do this. So this is the one case. And the other case, when it would be over full, I cannot pour in more than what fits in at the very most. So we could imagine now I will say a few more concrete details on the pouring because I skipped that before. If I can fully pour from left to right, I'm okay. But if the right class will be full at some point, my rules now that I'm introducing saying is, okay, I pour as much as possible into the right class, and then the right class is full, so capital Y. But what I cannot fully, or from the remainder that I cannot fully pour, I'm stopping, and I keep this in the left class. So I'm not pouring over, so that it swaps over, but rather what the remainder that I cannot pour, I will keep in my left class. So what I'm saying is, I take my filling of the left class and I subtract something. And what I'm subtracting is the difference I could pour, because there is a difference in how much still fits in the right class. And this is the capacity of the right class, capital Y, minus the filling of the right class. This is how much I can still fill into the right class. And this is how much I'm pouring in. So I'm subtracting it from X. And then I have something left in the left class, but the right class is full. So I'm putting in Y. This is the action to pour from left to right. And we're now doing exactly the same that we pour from right to left. If we pour from right to left, we put in the left class what was there, X plus Y. The right class is empty. And I can only do this if X and Y are less than or equal to X, because that's how much fits into the left class. Where I'm pouring with the first case, that's how I can pour, because there's enough capacity, enough left in the left class, so I can pour it in. But if this doesn't work, so that the left class is completely full at some point, I'm putting in a capital X, and in the right class, I only pour out, or from the right class, I only remove how much actually fits in. So this is capital X minus X, how much I can still fill into the left class. And that's when I'm subtracting from the right class, and the left class is full. And my action, I write pour from right to left. And these are the two actions I have done now. I know this looks complex, but it will be more obvious now when we try out our example. What I have now is, for my pouring problem, I have everything at hand I need. I have my isGoal function, I have a successors function, and I have my start state. So let's try it out. I'm going to call the shortest path search, and I'm passing my my start state. The last element I'm passing is a reference to the isGoal function. So remember, I'm not calling the isGoal function, but I'm passing a reference. What looks a little bit different is the middle one now. I'm calling the successors function, and I'm passing the capacities. And remember, when I call the successors function, it only returns a reference to the inner function. So when I call the outer successors function, this returns a reference to the inner function, and the inner function can use these capacities, and I have defined them now. So now I have run it. Let's look what's inside. I can look what's the length, or maybe let's print res. Let's see what's in res. I get something quite long. As you can see, it actually, the res starts with 0, 0, then it fills the right class, and the right class is filled. Then it pours from the right to the left class. Then it empties the left class, and so forth. So it keeps doing a lot of steps, ... We can also print out the whole result. And we see eventually, after a lot of steps, it ends into 6, 0. And this is our path that we had stored in the frontier at the end, or that we had increasingly built in the frontier. And it actually takes a lot of actions. We can also look at its length. The length of res is 1,237 elements. But remember what its structure is. It starts with a state, it takes an action, then it has a new state and a new action. So if I want to know the number of actions I took, I need the res, its length, and divide it by 2. But here's the problem. It gives me some float value, because in Python 3, this gives me a float value. So I can convert this to an integer, and then it's 618. And you can also write this in Python 3 in a different way if you wish. You could also write it something like this. It's exactly the same in Python 3. And what I see, it took me 618 actions to get from 0, 0 to 6, 0. And this is the shortest path. We can try a few more examples. For example, with different start states. I don't need start state as a variable. I can also just put in 0, 0 as before as a tuple. It's the same. But I could, for example, start with 0, 6. And I want to get to 6, 0. And we're not going to store this in res. We directly print it out. So if I start with 0, 6 and I want to get to 6, 0, it's fairly easy. It's just one action because I pour from right to left. We can try a few more things. And for example, we can also change these capacities. So I want to go from 0, 0 to 6, 0, but I change the capacities. For example, this is 400, or say 312, and this class is 420, for example. And I want to see how long does it take? How many actions do I need? And it turns out this path is empty. That means this search problem is not solvable. So I cannot get from 0, 0 to 6, 0, because 6, 0 is hard-coded in isGoal with these capacities. It's not solvable. We can try out some other settings. We can say this is maybe, I don't know, 422. We can see if that, or say 421, and we see if that's solvable. And we see there is some result. Let's see how long it takes. It takes 592 actions to get from 0, 0 to 6, 0 with these capacities. One last thing before we're finishing this example. I'm just going back to the code from before, and all of this is available also in the course worksheet and in the zip file. Before, I had hard-coded this isGoal function, and I have passed the reference. I can make this a little bit maybe more generic, because I don't need to explicitly define the isGoal function. What I can do is I can use a lambda expression. Who of you has worked with lambda expressions before? Maybe positive or negative reaction, if this is something you have seen. A lambda is just an implicit function that I'm creating. So before we used explicit functions because I defined, I said def isGoal, but a lambda is an implicit function definition. So I'm just writing lambda state. This means this function has a parameter state, and I'm checking now if that state is 6, 0. So I don't need to pass a reference to isGoal anymore. Rather, I'm implicitly creating this lambda function and I'm passing a reference to that one in here. So I can more easily customize this. And we can try this out. Say we had 418 and 986 as the capacities before. And we wanted to get from 0, 0 to 6, 0. Maybe we want to get to 20 and 8 and see if this is solvable. And we see this is actually not solvable. We cannot get from 0, 0 to 28. It's impossible. Maybe we can try 20, 0 if this works. This actually takes the fastest number of actions is 188 actions to get from 0, 0 to 20, 0 given these capacities. So we have now solved the first coursework problem, and we can just take a peek at the coursework sheet again. So this was problem 7.1. We had these capacities, the start and the goal, and this is exactly what we have coded together. The only difference is I put it in a separate file and I imported the shortest path implementation from that other file. We had just written this now in one file or in one interactive environment. And I've only put this here in case there's main context. So in case you're running this file that I have described here, but this is just minor changes. It doesn't change the logic at all, because you should always separate your code into multiple files and put in some structure. But here we've just coded it in this interactive environment. Do you feel confident with this shortest path search now and the pouring problem? Maybe some indication, thumbs up, thumbs down, or if there are any questions you may have. I know this was not easy because we have built this highly generic shortest path search, and it's totally independent of what kind of search problem I'm solving. Because I just work with states, I work with successors and an is-goal function, and I'm using all of this in the shortest path search. And then for a concrete problem, I can define what the states look like. For example, a tuple, could be also other objects if you wish. We have a successors function and the is-goal function, and I only need to write them for my specific search problem, but I don't need to worry about the actual search anymore. So I'm separating the generic search from the actual problem. The search is generalized, and in my concrete search problem, I don't need to worry about the search anymore. Because when you try to code something like this on your own, when you're a beginner, you would often write a fairly complex algorithm mixing up search and the problem. And this leads to a lot of challenges. Often it doesn't work. Often you need a lot of time for debugging and somehow fixing it. And probably one point you get it fixed, but you cannot reuse it. And here we can reuse the search. The search has nothing to do with my concrete problem. And for the concrete problem, I'm writing a successors function as well as an is-goal function, and I define the state format. For some problems, writing your own successors function is maybe easier, sometimes more difficult. You need to think about a different state format for your problem and the goal function, but you never have to worry about the actual search again. In the coursework, there is a more complex search problem. It's called the missionaries and cannibals. It's described in here, and you can try to solve this at home during the weekend or next week in the lab session, because next week we're actually having the regular schedule, labs in the mornings and afternoons, and then the lecture in the late afternoon. Maybe you can try to work on this in the lab sessions. But first of all, make sure you have understood the pouring problem, and then try to work on the missionaries and cannibals. The only thing you need to do is write a successors function, think about a state format, and the is-goal function. Writing the successors function, however, is more complex, and maybe you cannot build the dictionary in one go. Maybe you need to first create an empty dictionary and that add element per element, depending on some conditions, and then return the dictionary. I had shown you this before initially, how to do it. Could be easier to solve this then, but it's doable. It just takes you a little bit. And there's a hint, maybe this itertools function can be helpful when writing your own successors function, but it's not a must. I only found it helpful to use this for thinking about various combinations in this missionaries and cannibals problem, but this is totally optional. It's up to you. It's just a suggestion that could make it easier, or maybe not, how depending on how you write your successors function. So one thing I missed so far, and I want to explain this now, is that the shortest path algorithm we had looked at is an uninformed search algorithm. Uninformed in the context of such search algorithm means that all the costs all the actions have the same cost, so there's no different cost per action. And in the algorithm we have implemented, we cared about optimizing for the number of actions or the number of hops from one state to the other. But which action we take doesn't make a difference. There's no action is more expensive than the others. So filling, pouring, emptying all have the same cost. Now we could think about varying these costs. We could say filling is more expensive than emptying. And then we need a different algorithm. We need a so-called informed search algorithm. And that one needs to take into account the cost per action and also the total cost of the frontier, of the paths, and then also manage the frontier in a different way. This is what we will do now with the lowest cost algorithm. It's an informed one, but in between, if you have some time over the weekend and you want to see how you can also find the shortest path in a maze with, for example, water or electricity. There's a very interesting video I recently came across in YouTube that uses water or electricity to find the shortest path in a maze. You can also find the shortest path in a maze through through the algorithm we have defined now, because you could just think in terms of states, and then you have successors, which action you can go next in this maze. And then you can try to solve the maze with your highly generic state search. And there's also electricity and water towards solving this, which I found quite interesting. So the video has nothing to do with our algorithm. It's just a completely different approach how to solve a maze, which I found quite interesting. Maybe you want to watch the video. It takes like 22 minutes and overall worth watching. Now we will assign costs to an action, and this will be done by an informed search algorithm that we call the lowest cost algorithm. And the lowest cost algorithm looks a little bit like the shortest path, but it also contains a few different aspects, because we need to then not optimize for the number of actions, but for the total cost. And if different actions have different costs, maybe it could be cheaper to take more cheap actions than one expensive action. And this is something we will implement now in the lowest cost algorithm. And I will again do a live coding session so you're able to understand it step by step. In our algorithm that we call lowest cost search, we have again a start state, a reference to the successors, and a reference to the is goal. So all of this is exactly the same as before, but we have another function reference that we call action cost. And action cost will refer to the action or to the cost per action. And like this, we can then we can calculate the total cost. And that's something we also need to store, because then the number of actions doesn't matter too much. It's the total cost. We also need an explored set. This time there are a few steps that look the same as in the shortest path, but lowest cost is still a little bit different. The frontier is the same. We are putting in our start state, and we put that as a path, so it's a list in that frontier list. And again, we need to check We can do this as long as there is something in the frontier. We again take the leftmost element of the frontier because this is the lowest cost path. Now the frontier is sorted differently, and the frontier is not always just appended at the end, but we rather need to put a path in the right spot in the frontier, and the frontier is sorted by the total cost. But initially there's only one path, so that's the lowest cost path, and it's just a path that starts with the start element or the start state. I take now the final state. Well, in the slides, I have created a helper method for state 1, but we can also just say, as before, we take path at element -1. So just the rightmost state is the one we care about. For our initial toy path, it's just this element. And I'm checking here if that path or that element I'm actually looking at, if that's the if that is the goal, and if so, I'm returning the path. So this is more or less what we have also done before, but the isGoal check is here moved, and I'll later explain you why the isGoal is moved here and not where we're doing the expansion, and you'll see this later why the goal check is here and why there's only one goal check and not two goal checks like before. But we're checking at this point if that path or the last element of the path is the goal, and if so, I'm returning that path and I'm done. If I'm not done yet, I'm adding to my explored my new state I'm investigating, and I need to calculate now the path cost up to here. And for this, I have a helper method that I call path cost. I can add or I can pass a path to path cost, and it calculates me the total cost of the path. How to do this exactly is something we will be seeing later. And then I'm going through the successors, again, state action pairs in successors for this state and the items, which is the key value pairs. And I'm checking if the state is not in explored yet, because if that state from the successors is already in explored, I don't want to explore it again. It's already looked at like before. So this is something this algorithm has in common with the one before. But now I need to calculate the total cost of this path, and the path cost or the total cost is the path cost up to our past state. Now I'm looking at the successor, so I'm adding on top the action cost when going to that successor, and action cost is also a function, and for this function I pass an action and it returns the adequate cost. So that function will just return some integer or float value, and for a specific action could also be implemented in terms of a dictionary if you wish, but it's up to you how you implement action cost. And then you're returning that cost of taking that action, you're adding it to the path cost, and you have the total path cost now. The paths, they will be a little bit more complex than before, because what I'm adding to the path is now not just a list of an action and a state anymore, but rather I'm taking that action, and when I take that action, I have a total cost, and then I go to my state from the successor. So I'm adding actually also two elements here to my path, but I'm adding a tuple. That's the first element, which is the action and then the total cost, and then that successor state. Now I have my new path by taking the last element from the previous path, taking that action from going to that successor, which comes with a certain cost. And now I need to do something quite different to before, because before I could just add that new path to the end of the frontier, because the frontier was only sorted by the number of actions I took. And if I took one more action, I could just add it to the end. But this time, the frontier is sorted by actually the total path cost. And here I cannot just necessarily add something to the end of the frontier, but I may have to put it somewhere in between that frontier. And that's why I have a helper method or a helper function to do this for me, because I have the frontier and I want to add path 2 into the frontier at the right spot, assuming the frontier is sorted in an ascending order in terms of the total cost. And if I eventually complete this loop, I will also just return a fail. I could define fail. That's what I've done in the slides. Fail would be an empty list, or I just do it here. So I'm just returning an empty list, because if this loop ever finishes, that means I haven't found a solution. So there are a few differences of this algorithm compared to before. I have one more parameter, which is an action cost. I have moved the isGoal check. Before, the isGoal check was when I looked at a state among the successors and I said, well, is that the goal? Then I'm done. Here I cannot do this because I need to add this to the frontier, and then I cannot complete when I have maybe found, or when I assume I have found the goal here where I'm marking, because there may already be something added to the frontier with a shorter total cost that brings me to the solution or to the goal. So here I cannot do the goal check because it may actually lead to a wrong result, but I need to move the goal check always to when I pop something from the frontier. And actually I noticed I made a minor typo, which is done because this would lead to actually quite a different algorithm, but it's correct in the slides and a code that I'm providing to you. It's pop 0, because a pop would actually take the rightmost element. That's what I don't want. So the pop 0 is actually correct. But in case there's any other typo, which I don't see, you always find the correct code in the slides, because in a live coding session, sometimes something may just go wrong because it's live, but now it should be correct. So this this goal check has been moved, and because it's been moved to up here, I don't need it at the beginning anymore, because in our shortest path, we also had a goal check in the very beginning of the code, and we checked if the start is already the goal, but I don't need this anymore because I do this now at the beginning of the loop when I take something from the frontier. And I can simply check it here then, so I don't need to check it twice. This is the actual difference between lowest cost and shortest path from before. There are two helper methods that we have not implemented yet. What we need is the path cost. That's something we need to implement, as well as the add to frontier. I'll quickly show you how to implement the path cost. It's a helper function, so I've moved it. And what we see is we add the total cost by taking our past path and adding these two elements. So we're adding a state, and we're adding this tuple of the action and total cost. So I need to access this tuple, and in the tuple, I need to access the total cost. So what I could do is I could say, well, I'm taking the second last element from the path, because this is -1 and -2 is this tuple. So, and if it's a tuple, I can break it into two parts. So I have two variables, action and total cost. because -2 gives me this tuple, and I break it into action and total cost, and I could be returning the total cost. This looks like it works, but it will not work when you run it for a short path, because the initial path only has this one element. And if that's the case, I cannot just access element -2, because for my initial one, where I have this short path and I want to calculate its path cost, if I take the element -2, this will lead to an exception because it's an invalid index. So I need to add a special case. I need to check if the path length is -3, meaning I just have a very short path from initially, then the total cost is just 0 because I have not taken any action yet. This would be the case just for what I have added initially to the frontier. And then I'm returning a 0. Otherwise, I can just leave it like this, or in order to make it more obvious, I'm putting here an else, but it would have also just worked the other way with the, like I had it just before with the return 0. And then I have implemented my path cost. There is one method that is a little bit more complex to implement. It's the add to frontier. And I somehow need to add this path to the frontier. This is something I will briefly show you where you can find it in case you want to implement it on your own. So this is the lowest cost algorithm we have just done, and we have discussed the path cost. The add to frontier is a little bit more complex to implement. And we're not discussing it in detail in the lecture. You're welcome just to use the code as it is. It's provided to you in the zip file for the lowest cost implementation, because the implementation I have here, it's relatively inefficient because we don't have the tools at hand yet how to implement something like this efficiently. And that's why for now, maybe just use the add to frontier as it is. It's probably inefficient, but in a few weeks' time, you will learn how you would be implementing something like this more efficiently. So there's no point now in discussing in detail how to implement an inefficient algorithm. Rather, just use it for now. And in a few weeks, we're discussing how you could, or we will discuss a more generic algorithm of how something like this could be done extremely efficiently. But right now, we're not there yet, but the code is available for you in the zip file. There is no specific coursework for the lowest cost algorithm, but this coursework is anyway very free, so you should take your own direction and not just, solve the same problems over and over that others have done for the last few years. Maybe just try to amend this pouring problem, use the lowest cost algorithm, and add some cost to a specific action. Maybe filling is more expensive than emptying a class. Try to amend this, come up with your own action costs and see what you can observe. And maybe you're able to create a situation or an instance where you have a lot of actions, but it's overall cheaper than if you just take a few very expensive actions. You could say, for example, filling costs 1, or say filling costs I don't know, 100, but pouring just costs 5 and emptying costs 1. Maybe try out what could happen from this and try to play with the numbers and see how all of this behaves. This is probably one good way how to practice this. So here are also the differences to between lowest cost and shortest path. I had mentioned them already orally. And again, why are these two highly generalized search algorithms so interesting? Because we can separate search from the actual problem. They're highly generic. They don't care about what the state actually looks like. They only care about what a frontier and paths look like in terms of their structure, but what's in which states, it doesn't matter, because all of this is handled by the successors and isGoal function or the action cost in the last algorithm, and you define the state format. So it's a very good separation and allows you to reuse the search for many, many different problems. And I invite you to think about some new problems to which you could apply this generalized search. You can use this for routing, obviously, too. There are other algorithms for routing, like Dijkstra, but I wanted to discuss a highly generalized approach to search with you, because you can apply it for much more than just routing. This is so far the generalized search. This generalized search I found many years ago in some, or at least an inspiration for this in a Coursera course from Peter Norvig and I think Sebastian Thrun. Or it was not Coursera, it was an online course, Udacity. It's a different platform. And I got inspired by this, but I've also amended it a bit to make it work for our course and added some explanations. But I think overall, it's something really cool that you probably don't see in a lot of other algorithms and data structures courses, because they are concerned just about routing. I'm concerned about a much more generalized search problem. And the beauty of these two algorithms is you can reuse them to many or for many, many other problems if you wish. So I invite you to try this out. If you check the literature, there are much more search algorithms on graphs. There's not just lowest cost, shortest path, or Dijkstra. There's also an algorithm that is called A-star. A-star is something you would often see in an introduction to AI course, because this is an algorithm that is somehow very much of interest to the AI community. And we're not discussing this algorithm here in detail, because I don't just want to do search with you. And we have now built these highly generalized search algorithms. But if you want to learn more about A-star, it could be, for example, discussed in an introduction to AI course. Maybe send me some positive or negative signal if you have seen A-star so far or not. But A-star is not of big interest to this course. Just a few words about A-star. A-star is an informed search algorithm. So again, takes costs into account and has the goal to expand the path, which has the minimum value F. And F combines two things. F has this current path cost, so this total cost we have seen before. And H is some estimated distance to the goal. Concretely, H is a heuristic function, and A-star takes advantage of a heuristic, and it's guaranteed to find the lowest cost path if the heuristic is less than or equal to the actual true cost. And the benefit is that that this gives you the lowest cost given this heuristic. And if H never overestimates the real cost, then it's called an optimistic or admissible heuristic. One could think about this just from a very simple example. Say I have a start state and I have a goal state, and I want to solve this maze. I have valid states that are here which are transparent, and the black states are I cannot enter. So this could be a wall, and the heuristic to this could be actually just the true distance in terms of the actions you need to take. For down here, the difference is 1. For down there, the distance is 2, and so forth. And this could be a very simple heuristic of what's the distance from your current state, so from this state to the goal, how many steps you need to take. It would be 3 from here, 4 from up there, and so forth. This would be a heuristic that is optimistic because it doesn't overestimate. Overestimation would be an example. If you put in 5 in here, then it overestimates the true cost because the true cost is 1. You could underestimate. You could obviously change this to 0.5 or just 0. That's fine. And then the A-star algorithm is still guaranteed to find you the shortest path, or in this case, the lowest cost path. But we are not discussing this here in this course. It's something that is often more of interest in an introduction to AI course, which we're not teaching here. If you take a look into the AI book of Peter Norvig and Stuart Russell, they discuss A*, for example. So maybe just take a look there. I also want to share a few best practices for graph algorithms. We have seen today why it's so helpful to separate between the general search and the problem-specific properties. So you can reuse this algorithm to many problems. If you have any state search problem or search problem, think about if it can be addressed by our generalized search algorithm. And then all you need to do is you can reuse these algorithms and provide your own implementations of the successors and isGoal function and define your state format. And it turns out that a lot of computational problems are actually, or a lot of algorithms that you come across or problems that you face actually have to do something with graphs. And if you're trying to solve some algorithm problem, ask yourself if you can address this computational problem as a graph problem. And if you can, then maybe there's already an algorithm available for you. What I like on Wikipedia is there's a huge list of algorithms, and there's a huge subsection on graph algorithms. I invite you to take a look at this, and you will see there are a lot of graph algorithms that have been proposed. There are obviously other lists as well, but I like the list on Wikipedia. And maybe for your computational problem, you can just reuse an existing graph algorithm or amend it to some extent, and then make it work for your own problem. I have faced this quite a few times in my career. I faced some challenging computational problem, and I was able to pose it as a graph problem, and then I was able to solve it fairly easy. I have come across this, for example, the first time in my bachelor's when I did a mandatory internship, which you also need to do in the course of your bachelor's. My bachelor's program was just in general computer science, not in AI or anything like that. That didn't exist at that time. And I did my mandatory internship at SAP at their headquarters in Walldorf. And I was in a team that faced a computational problem, and many of the colleagues at that time, they had some idea how to solve it, but they had some algorithm, and they sort of tried to tweak it to specific instances of that problem, but it was all quite messy. And I actually proposed then that this could be seen as a graph problem, because the problem did not directly look like a graph problem, but I was able to pose that computational problem as a graph problem. And then there was an existing algorithm, in fact, the topological sorting. And I used that, which is, I don't know, 20 or 30 lines of code, and I amended it and added business-specific rules to it, which was maybe 1,000 lines of code, adding all these rules from that business problem. But then the problem could be fairly easy solved, and it worked reliably, and the graph algorithm did not require further amendments just for specific instances. Rather, I described all this business logic and added it to the topological sorting, and we could solve that computational problem in a highly generic way by adding also, we had to add some business rules, obviously, because the topological sorting didn't fully work or didn't fully do what we wanted to do. We had to tweak it, but I was the one who discovered that this was actually some sort of graph problem, and then the problem was solved once for all by just massively enriching the topological sorting. And that's something that I proposed in my, I don't know, second year of my undergrad. So if you go into industry, take advantage of that opportunity. And especially if you come as an outside person, maybe you're able just to bring in new ideas that the team maybe didn't think about anymore because they had just been in their own bubble for too long. And I posed that problem at SAP. It was also something about dependency resolution in a scheduler, like when to run certain procedures in a scheduler, but there was lots of logic around it. And I posed this as a graph problem, added business-specific rules, and actually worked fairly well. And I guess SAP still uses this today to some extent in one of their software tools. So take a look at this list of algorithms just so you're a bit familiar with what's actually in, and maybe for your own problems, there's something you can use and amend, and you don't need to start from scratch. We have now finished this graphs chapter. It was probably the most generic algorithms we have discussed because we've dealt with highly generic state spaces, and but I think it's a beautiful approach to solve a lot of search problems. And what we are now looking at for the remainder of today is complexity analysis. Complexity analysis means we want to describe how complex an algorithm is in terms of its running time or in terms of its space that it needs in the memory. And concretely, we will discuss time complexity and see why this is a very important measure of an algorithm. We look at various notations. The most famous one is the O notation. Some of you may have seen this before. Who of you has ever seen like an O notation, like O of n, O of n squared? Maybe green sticker if you have, or red if you have never seen something like this. It's maybe discussed for a short moment in a programming class or an introduction to computer science. But in this course, we go in very deep. And the ones who have seen it, maybe you can just write here in the chat where you have seen this, if this was in one of the other classes or in your private studies. So just let us know where you have come across this O notation. In this course, we will dig very deep into it. And the time complexity is actually something super important that we need in order to build efficient algorithms. We'll discuss it here. There are other notations like omega, theta, O, O tilde. They are all also important, but probably the O is the most common one. We'll be looking at the other ones as well. And we got an answer here from a student that this was discussed or introduced in the mathematics class. In this course, we go very deep into it and we analyze algorithms. In a few weeks' time, we will even look into recursive algorithms and see how we can describe their running time complexity. And this whole framework we are building today can not only be applied to time complexity, but also to space complexity. So how much space in the RAM your algorithm would need. Now, I'll have a quiz for you, and I want to know from you how long, or how would you measure how long it takes to run some algorithm? If you have any suggestions, maybe turn on your microphone, share your thoughts with us, or let us know in the chat, how could you measure how long it takes to run some algorithm? Maybe it takes 5 seconds or 10 hours. How can you measure that? And I'll give you a moment to think about this. Or maybe just send like a thumbs up if you have an idea, so that I'm not waiting for anyone here in case there's nothing coming in the chat. If you have an idea how this could be measured, thumbs up. If you have no idea, maybe thumbs down, and then I'll see. So one student says we could count the amount of operations executed. Yes, that's something actually quite reasonable. But maybe some operations take longer than others. We could maybe just count the lines of code. Maybe this would be the number of operations or the number of statements. But maybe just this takes, maybe some operations take much longer than others. And I'll show you now how we can measure this in a computer program, actually. We will in Python, and you can do it similarly in other programming languages. You can import that from the time module, the time function. And what it gives us is, we can just call time. We see it gives us something, some strange number in here. And if I call it again, it gives us a new number. And in fact, what this does is it counts the number of seconds. So that's why it's a float. So dot something, the number of seconds since a reference date. And this reference date, you may see if you look into the documentation, or in this interactive environment, you can just put a question mark behind it and press enter. And it says it returns the current time since in seconds since the epoch. And this reference date is in many systems the 1st of January 1970 at midnight at UTC time zone. So if I run it again, we see this is growing. So I could try to measure the running time the following. I could measure the time. I'm now writing multiple statements, and I could put in some loop, for example. Say this is a loop. I run this 10,000 times, and I square I, just like this. I, after the loop, measure the end time. And then this all gets run. And then I can see how much time this took. I can say, well, the end time will be larger because time keeps growing, minus the start time. And I see this took like 0.01 seconds. We can maybe make this a little bit more complex and add something like this, then run it, and then compare again. And we see, well, this takes like 28 milliseconds or something like this to do this 100,000 times, these operations. So this is one way how we can measure running time. One student here wrote in the chat, we can also use a profiler. Yes, a profiler is a very helpful a very helpful tool, because with a profiler, I can measure the running time of a program, and the profiler will show me in which parts of the program I have spent most time in. And then I can maybe go at a couple of lines or a couple of functions in which I've spent most of the time in, and I can try to optimize them. And measuring running time could be done, as I have just shown you here, with this time module and the time functions. If you look at other programming languages, this works fairly similarly in Java or C++. You just need to use the right package or library, and then this is done. How to do this is also here in my slides. And I think, well, this overall looks reasonable. But it isn't that easy. There are lots of challenges when doing such an experimental analysis, because when I run this experiment twice, I will get different numbers, because maybe I'm running something in the background in this computer, depending on how much time the operating system assigns to my processes or threads. It runs faster or slower. If I run the same experiment on two different computers, I'll get different results, because I've used different hardware, different software environments. And also, I can only do this on a limited set of test inputs. And if I have some more complex algorithm, not just in here, doing some multiplications, but something more complex, I have a problem, because I'm just unable to test this on an adequate number of inputs in order to measure how good or bad it is. And on a different computer, it may behave differently. And also, if I have some theoretical algorithm in mind and I have not implemented it yet, I'm also unable to assess its running time, because I need to implement it. And maybe I'm unable to implement it, or I don't have the data for it that I need. So all of this will make an experimental analysis complex. So we need something different. I'm not totally against experimental analysis. Experimental analysis can be helpful in order to see how long it eventually takes. And maybe your customer requires that a certain computation must be run in less than a second. Maybe you don't want to let the customers wait in front of a user interface, whatever. But just thinking in terms of running time will not get you anywhere. It's maybe just something as a final check or a customer requirement, but don't try to start optimizing your program for running time. With a profiler, you will find very quickly the crucial parts, but there's also some saying that premature optimization is the root of all evil because maybe you're just focusing on the wrong points. What we are doing today is, well, we'll come to a mathematical approach in a second, but we see there are lots of other things that impact my running time analysis. Hardware, which CPU, how much RAM, which caches, my operating system, what else is running concurrently, my scheduler, swapping. So swapping means I run out of RAM and I need to move some of the data from the RAM on my hard disk. It's super slow, even with solid state drives nowadays. Swapping is something that will severely limit me. And because swapping is much slower than using a RAM. Caching is also something that matters. For example, caching not just in the hardware, but also in the operating system and so forth. So all of this will have impact on my running time experiment. I could also be thinking about, I have some algorithm and I can put in a problem, maybe for example, a sorting algorithm or whatever, and I can put in different test sets in order to measure how long it takes to run in milliseconds. And I see, well, somehow this grows linearly if I put in more data. But here I have a data set that has 6,000 entries, and I run the same experiment multiple times. And in fact, I get different numbers because there are all these reasons for variation. While I talk more about this, maybe the student who wrote me in the chat that you discussed this O notation briefly in the Mathematics 1 class, maybe tell me what you did with that in the mathematics class. And I know you are from all different sorts of degree programs, so not everyone will have seen this in the Mathematics 1 course. But maybe you can write us briefly in the chat while I talk here what you use this for in your mathematics class. So we see there is, and now it's more or less just mentioned in a side note. So good, you're here and to compare functions. So you're here in the right place to discuss this in depth with me this week and next week. And actually we'll be using this O notation throughout the whole course. And we see there is some linear trend in here, but it's not very reliable because there's huge differences in running times for the same size of data set. Maybe for a different data set that has the same size or the same data set. So this is not very reliable. And if you run it on a different computer, maybe with larger caches, larger RAM, it runs in a different amount of time. So we need a totally new approach because we want to be able to evaluate the efficiency of an algorithm and like this, compare the efficiency of different algorithms completely independent of the hardware and the software environment. All we want is to study a high-level description of the algorithm. Can be pseudocode, obviously it can be also a concrete implementation. And we just look at the description of the algorithm, but we don't need to implement it for our analysis. So it can be purely a theoretical algorithm or a draft. And we want to be able to compare the so-called complexity of these algorithms and then pick the one with the better complexity. And we not just want to take into account one or a few possible inputs, but ideally all possible inputs. So not just a limited set, but everything you could ever put in this algorithm. And we're now building a theoretical framework in order to make it there. What we're doing is we will count so-called primitive operations. Because one student before proposed, we take into account the amount of operations executed. So we will be counting primitive operations. We'll see in a moment what they are. Then we want to describe count the number of operations this function takes in terms of the input size, because we put in some input in our algorithm, like a list, for example, and depending on the size of the list, the number of operations may vary. And we always care about the worst case input, not the best case input, the worst case input. And there are good reasons for that. So what are primitive operations? There are lots of simple operations in a computer program that we call now primitive operations. Could be, for example, comparing two numbers, performing an arithmetic operation, assigning some value to an object or a variable. For example, in Python, we could also index a list. So we use a regular list and use an index. And because here we can do this, actually the index number doesn't matter because it's also a primitive operation, maybe calling a function or returning from a function. And this whole thing of accessing a list is something we'll be seeing in the next chapter, but we just assume a standard Python list that is based on arrays or returning from a function. All of these are simple operations. And there are obviously many more. And we assume that these primitive operations, they all take the same amount of time, or it's somewhat constant. Obviously, maybe assigning an identifier to an object could be cheaper in terms of the nanoseconds than comparing two numbers. But we just assume that they are all somewhat constant and they all take somewhat the same amount of time. In a concrete CPU that may be slightly different, but we don't care about that. It's an abstraction. And we will now not try to determine the exact execution time. Rather, we want to count in our program how many primitive operations are executed. And this operation count will somehow correlate with the actual running time in a specific computer. A specific computer may vary because it depends on the hardware and on the software, but we just care about the number of these primitive operations and how it depends on the size of the input. And that's what we're doing. We will always think of algorithms now and describe them as a function f of n. So we pass a value n, which or an input n, could be a list, for example. And depending on the size of the list, we may need a different number of primitive operations or not. Maybe it's independent, maybe not. We'll be seeing this. So our function f of n will depend on the size of n of the input. And it's not just a list, can be other inputs obviously as well. But maybe for now, we just imagine it's a list. And we want to see if the number of primitive operations depends on n or not. And if it depends on n, we will describe how much it depends on n, if it depends very little or a lot. And we will be focusing on the worst case input. Maybe for a sorting algorithm, we want to sort a list. Maybe some lists are easy to sort while others are more difficult to sort. And we will always focus on the worst case input. And because our belief is, and this is actually an assumption that holds true in most real-world settings, if we optimize our complexity, so the measure in terms of the n, the measure of the number of primitive operations depending on the input size, if that is optimized for the worst case input, most times it also works well then on other inputs. We could do some more advanced stuff like average analysis, so on an average input, but then you have to make some assumptions about the probability distribution of the set of inputs. So for now, we just care about the worst case input. We will see a few times in this course maybe the best case or an average case input, but there you really have to make a lot of assumptions about the distribution of the inputs. So we just care about the worst case. Because what could happen here is we have different inputs, A, B, C, D, E, F, G. We have the worst case inputs A and D, and they take the most running time, while other inputs like E, take the best case, but then there are some in between like B, C, F, and G. And here we would really need to make some assumption about the average input in order to find the average case time. And that's tough. Sometimes it's done, but maybe that's something more advanced. We will care about the worst case input, optimize for the worst case. And if that leads to better algorithms, typically that leads to better algorithms for many or for most other inputs. In order to build our framework, we need a couple of basis functions. And these basis functions, they are, first of all, just from mathematics in high school. So we quickly go through them, and then we'll be using them in order to build our mathematical framework. A constant function, and I assume you have seen these functions before because they're fairly easy from high school. And they're not really advanced. We have the constant function, and a constant function is independent of n. It just returns a constant, and a constant could be a small value like 5, it could be a small value like 27, or a larger value like 2 to the 10. These constant functions are independent of n. And the interesting thing is we don't care about the exact constant value. If the constant value is 5 or 500 or 1,000, we don't care. It's just constant, and it doesn't depend on n. So if n gets large, that constant doesn't change. In reality, obviously, a large constant, say 50 primitive operations, takes probably longer than 2 primitive operations, but the impact is negligible, because we care always about large worst case inputs, so n gets big, and then it's negligible what that constant is. In reality, yes, if you have a strong CPU or you can take advantage of parallelization, yes, these constants probably have some impact, but we don't care about them. It's just an abstraction. And oftentimes you will just then write a C for a constant or just a 1 for the constant and not 27. We'll see this later when we do such an analysis. But it's independent of n, which is most important. We also have a logarithm function, and a logarithm has a basis. Typical logarithms that you would use is a binary logarithm, a logarithm with basis 10, or the natural logarithm ln. And what you probably know or remember is if you want to calculate the logarithm n of basis b, you would just calculate this as the log n divided by log b. B is a constant, it's the basis, and log in this definition here, at least in this line, log would be the logarithm to basis 10. You could also just write ln for the natural logarithm. But in complexity analysis, we don't care about the basis of the logarithm, because log n of basis b is just log n divided by log b. Log b is a constant because b is a constant, and we don't care about constants. So all we care about is the log of n, not the exact basis. And what is very common in computer science is that we oftentimes use basis 2. So we only care about the binary logarithm because we deal with binary with a binary system. So the binary logarithm is the most common one that we use in this course. So oftentimes when we write log, we actually mean the binary logarithm. But again, the basis doesn't really matter because it's a constant and we don't care about constants. There are all sorts of logarithm rules that you know from school. Who of you feels comfortable with logarithm rules? Maybe thumbs up or thumbs down. Just curious to see who feels comfortable with them. Well, only positive responses. If you don't feel comfortable with logarithms, you need to revise them. That's certainly something you have learned in high school and is required for getting into university. There are some basis rules that you need to remember, like the log of basis b of a times c is the log of basis b of a, plus the log of basis b of c. If it's divided, it turns to a minus. This rule here is important. The log b of a to the c, you can move c down in front of this. Plus, there are a few other rules that are maybe something that you deal with less often. There are some examples here. So the log of 2n is the log 2 plus the log of n. And if we assume that the basis of the logarithm is 2, so the log 2 is just 1 because 2 to the 1 is 2. So we assume this is the basis 2, which I've also written here in the note. So this would be then 1 plus log n and so forth. So you are welcome to revise this, and you always see which rules we have used in here. If you have any problems with logarithms, every year there are some students who have not studied or don't remember them well, please revise them. Sometimes there are some high school students who take this course on the site. If you have not come across logarithms, feel free to study them. But if there are any problems with these foundations, there are also the lab sessions. So you're most welcome to come to the lab sessions, and I'll help you with that in case you struggle with the preliminaries, because logs are super important. We will be using them a lot to describe complexity measures in this course. And I don't want you to run into problems with the course if you struggle with these foundations, and especially since there are some high school students every year. I've had once some high school students, 14, 15 years old, taking this course. They didn't know about logarithms yet, so I just showed them the essence in the lab. Then there's the linear function. F of n is n, a fairly simple linear function. And it's also a basis function we need for our framework. You can combine this also with a constant. For example, the function could be f of n is 10n. Then we also don't really care about that constant 10. We only care largely that this function term will grow with n and not with the constant. The constant will have impact on the final value, but it doesn't grow, and we only care about what depends fully on n. There's also the quadratic function. F of n is n squared, so f of n grows much quicker than n because we square n, and if n gets large, then n squared gets much larger. Some algorithms fall into this quadratic function, other algorithms into the linear function, other algorithms into the logarithm area, and we'll later see how we can analyze an algorithm where it falls in. There is also the n log n function. So f of n is n times log n. And what this means is it's greater than n because log n is, and we always assume for large n's, log n is greater than 1. And then we multiply this with n. So log n times n grows a little bit faster than n because this part here, log n, is greater than 1 for large n's. But n log n grows a little bit faster than n, but much slower than n squared. So this is something you should bear in mind. Then there are other functions that grow much faster than n squared, for example, n to the third. So it's n times n times n. And we can think from here and generalize this about all sorts of other polynomials. So a polynomial f of n could be a constant plus a1 times n plus another constant times n squared and so forth up to a constant times n to the d, where n to the d is the largest part of the polynomial. And then the value of this polynomial, if you make n very large, will be largely determined by n to the d. So if you imagine d is 10, so n to the 10 will be the part growing or will be the part contributing most to our polynomial if n gets very large. And then we also don't care about the constants, because even if AD is a small constant like 0.1, this part here gets extremely big when n gets much bigger. So That's why we largely care only about the largest part in a polynomial, which is this n to the d, and all the other lower order terms in the constant are also irrelevant. They're not fully irrelevant. They still contribute to the number of primitive operations, but they don't contribute much anymore when n gets really large. There are various polynomials here, like f of n is 1. It's just a constant. F of n is n, or 1 plus n to the third. And these are some sample polynomials. Then we have our probably last basis function, which is the exponential function. And the exponential function is a constant b to the n. For example, and the constant b must be greater than 1 so that it's exponential. For example, 2 to the n. And if you make n large, the exponential function grows much, much faster than the other functions we have studied so far. A common base in our course in algorithms, we set b to 2. So 2 to the n, because again, we're dealing with a binary system. And there are a few rules around exponents that are, again, very important, like b to the a to the c. You can write this as b to the product of a and c. B to the a times b to the c is b to the a plus c. And b to the a divided by b to the z, it's b to the difference of a and c. So these exponent rules are very important. Make sure you remember them, because we'll also be dealing a lot with them. And now we can try to visualize all these functions we had looked at. And remember here, the plot is a little bit different to the plots you probably known to, because we see this exponential scale here, 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. So 1, 10, 100, 1,000, 10,000, 100,000, 1 million. This is the x-axis for n. And on the y-axis, we put the function value, f of n. And we see that this function here is the exponential function. It's at the top. It grows much faster than the other ones. And we are using this exponential scale here so that we can just write this, or we can actually visualize the plot quite well. Because if we used a different plot, just regular ticks on x and y, we would only see the exponential function very quickly, and the other ones wouldn't be there anymore for substantially large n. And we can just see how they actually grow. So the constant is just here on the x-axis. It doesn't grow. It doesn't depend on n. The logarithm only grows extremely slowly. Then we have the linear one. The linear one are these pyramids. So this grows, and the n log n is just a little bit more than linear, still more on top, but far smaller than the quadratic or the cubic functions. So this is just a comparison of these growth rates. And we will now be building our framework, and I'll tell you what the core principles of our framework is. All we want to know is, how does the number of primitive operations that the algorithm needs depend on n? So it somehow grows proportionally to n. We want to know how. We will ignore lower order terms and constant factors. I've talked about this a few times. So we will only care about the highest order term and how the function or the number of primitive operations depend on that. And that grows based on n. And we only need a pseudocode description of our algorithm. If we have a concrete implementation, that's okay, but we don't need that. And we will just count the number of primitive operations. And again, we assume all the primitive operations take more or less the same time. It's an abstraction, but it will severely simplify our approach. And all of this is independent of the concrete hardware or software. And we will now implement a short algorithm together, and we will discuss what its running time actually depends on. What I want is, I have a list that I call L, and I want to find its maximum value. Oops, sorry, I need to do this in IPython. And we will have a list like this, and I want to find its maximum value. So the list is unsorted, so I'm unable to take advantage of anything in there, but I need to go through the whole list and check what's the biggest value in there. One way I can do this, at least in a simple way, is I call this find max. I pass the list of data. I assume the biggest value is my first entry. I just assume this and say this is the biggest one I have seen. And then I go through all the values in my data. And if my value that I look at is greater than biggest, I update biggest with that current value. And eventually I return biggest. Are you okay with that implementation, or do you see any problems in there? If you think it looks okay, maybe thumbs up. If you have concerns about this algorithm, maybe share your thoughts with us. Maybe thumbs down or a red sticker, then I'll wait for you if you see any concerns in this algorithm. I only see agreements. Well, it doesn't work perfectly, because if my list is empty, then this would lead to an exception, because I'm trying to index value, or I try to go to index 0, but in fact the list is empty. So this would throw an exception. And here I say, well, the first entry is the biggest, and I go through all the entries. So I would go through again the first entry, but we ignore that. It's just a very simple way to do this, and I'm ignoring all these corner cases that the data may be empty, or that I'm looking at the first entry twice. I just don't care about it. Now I want you to think about where I spent most of the time on this algorithm. In this algorithm, where I spend most of the time on running this when the data gets big. If you have a suggestion, maybe you can turn on your microphone or share this with us in the chat. What do you think where I'm spending most of the time on? We got the right answer, the for loop, yes. I'm adding some comments at the back, and we're using this O notation. I will later explain you what the O notation means exactly, but O of 1 just means constant time. So biggest is the first value in the data. This is constant. It's a primitive operation because it doesn't depend on n. Then the last statement, I'm just returning a variable or something. Then I can also say this is O of 1 because I'm returning something. And in fact, in the first line within the function, I'm actually doing two things. I'm accessing the data at index 0, and I'm assigning this to a variable, and I have to create a variable. So I actually have multiple constant operations in the first line, but it doesn't matter, because if I have 2 constant or 3 constant or 5 constant ones, we said we don't care. We only care about how all of this depends on n. Then the first for loop in here, there's a check, and this check is also O of 1. It's a comparison of 2 values, for example, integers. Could be more complex stuff, but we just assume it's integers for now. It's a primitive operation, and maybe the condition is true. If the condition is true, I need to update biggest. If the condition is false, I'm skipping this. So there's some primitive operations here to compare, and then based on the comparison, I do something or I don't. But I do this loop or these operations in the loop n many times. And also for the for loop, there's actually some primitive operations because I need to access the next element in data, assign it to value. I need to check if I have reached the end of data and abort. So there are some primitive operations around here, but eventually whatever the loop does, so assigning the next element to value or this check in here, that's done n many times. Now, if I run this for a small data set, just for, say, a data set with one entry, then the loop contributes to the overall time, but there are other things that we still notice, like the other entries before and after the loop. Imagine there could be some more statements there that are constant. But if I run this now for a huge data set, then the time at the beginning and the end doesn't really matter. It's just the loop that matters. So here we would say that the loop contributes most of the time, and we would say that this whole algorithm is O of n. We're coming soon to an introduction what the O notation actually does, but we see that for large n's, and maybe the worst case where I'm always just finding the next biggest value, because that would be the worst case, a data set that is just sorted in an ascending order, I would always have this condition true and then assign and not skip this because the next element is maybe smaller but bigger, and then I'm not skipping it. So this would be the worst case input, a sorted data set. And then it takes O of n. It also takes O of n if the data set is unsorted, whatever, because I'm going through the whole data set. But this part here is only true when I'm finding the next biggest element. And we're now coming to the O notation, and I'll explain you what's relevant about it. In the slides, we had just skipped this part, which I have live coded for you. Feel free to also run it, and then you will see that it actually returns the right result for our data set. And we are now looking at the big O notation. So it's a big O. Sometimes in the literature, it's an omicron, but we just use an O and pronounce it as the big O notation. We are often not just saying big O, we just mean O, and then everyone knows what we're talking about. And what we are doing is we have our algorithm that is represented by f of n. So the function that tells us how many primitive operations I have based on n. And I have another function, g of n, and g of n and f of n, they relate to each other. Concretely, we can say that f of n is O of g of n if this following condition holds true. The condition is f of n is less than or equal to c times, so this is just a multiplication, c times g of n. If this holds true for a c that is greater than 0, so c is a constant, and given for all n's starting n0, and n0 is greater than or equal 1. So it's a n0 is a threshold, and we'll soon see a figure what that threshold actually means. So for all n's, as of that threshold, if this condition holds true, we say f of n is O of g of n. It's pronounced just O of n. You wouldn't always just say big O, whatever. And what it actually means is that g of n is some upper boundary of f of n, because f of n is less than or equal to c times g of n for all n's starting a certain threshold. This can be visualized in this plot here. We see we have in dark or in black our function f of n, and c times g of n is an upper boundary given or as of some certain n0. Maybe not initially. We see maybe initially f of n is greater than c times g of n, but for all n's starting our threshold n0, f of n is less than or equal to c times g of n. So we see c times g of n, it's some sort of upper boundary because f of n is at the most c times g of n, or it's less. So it's less than or equal to c times g of n. This is exactly what I wrote here. So I say f of n is less than or equal to c times g of n for a real constant c that is greater than 0 and an integer constant n0. So n0 is that threshold or the input size, and we need to put in at least one input. Makes sense. And for all n's that are greater to or equal to that threshold, if that condition holds true, c times g of n is an upper boundary. And I have an example for you, which I think I will show you on the iPad. And it becomes more clear, and we will be busy with an interactive part. Notation. And I can say that this function 8n plus 5 is O of n. And you're wondering, why is this O of n? Because our condition was that, so this is our f, and this, or the n, is the g. And we say f of n is less than or equal to c times g of n, where we require that our constant is greater than 0 and n0 is greater than or equal to 1. And this holds true for all n's that are greater than or equal to n0. So this is what we had just defined. And now we can just, we only care that for large n's that are greater than our n0 or greater than or equal to our n0, this holds true. We could, for example, say that from our example here, that we can say our 8n plus 5 is less than or equal to c times n, because here we have the f, and there we have the g, where we need to find appropriate c and n0. Because we could say, well, if our c is 9 and n0 is 5, then yes, then this condition is true, because c is big, c times n, and our n0 is our threshold, and then this holds true. You could pick other choices. You could pick c as 1000 and n0 as 1000, and it holds true. You don't need to find the smallest c and n0 possible, rather just some for which all the subsequent n as of n0, this inequality holds true. So it's totally your choice how to pick them. And in fact, you can pick infinitely many pairs of c and n0 so that this inequality holds true. We can then look at a few more definitions, and then we'll actually be looking at examples, and we'll see what this is useful for. We can say that, or with this O notation, that our function f of n is less than or equal to another function g of n. We have this constant factor, and we say in an asymptotic sense, this grows, or Sn grows towards infinity, because we care about large n. For small n, we don't care, because for small n, this doesn't need to hold true, only for large n's. And we can also sometimes pronounce this in a different way. We cannot just say O, like f of n is big O of g of n, or O of g of n. Sometimes we can also say f of n is the order of g of n. It's the order of that. Sometimes what you see in the literature, some of you saw, you have seen the O notation before. Something is written that f of n is equal to O of g of n. Someone said that this was briefly discussed in maths. Have you ever seen that something was written like this? If you have, maybe thumbs up or thumbs down. This is something you see quite often in the literature. F of n is equal to O of g of n. This is something that is often written in the literature, but from a mathematical perspective, it's wrong, because this is not an equality. In an equality, you could flip left and right, but you cannot flip, you cannot write O of g of n is f of n, because actually O of g of n, what it gives us is a set. And that's why we can say, actually correctly speaking, f of n is an element in the set of O of g of n. So if you write it with an equal, this is often just written for convenience in the literature, but it's not an equality. So this is very important, because writing it the other way around doesn't make any sense. Some people, they just write f of n is an element in O of g of n. That's totally fine, but maybe looks a little bit cryptic. That's why people write it like this. But this is not an equality. It's just a notation for convenience. What I personally like to write it is, I say f of n is O of g of n, because it's in the order of g of n. Fully speaking, this element sign would probably be better, but that looks too cryptic. So I personally say f of n is O of g of n. But if you see someone have written it this way, then it's not an equation, it's just for convenience. In this course, when I created it, I tried to write it convenient or consistently throughout the course that f of n is O of g of n. If you find some occurrence where I didn't follow that convention, I'm sorry, but I tried to write it consistently throughout the course materials that f of n is O of g of n. If you see it, there are mistakes somewhere wrote equals, let me know, and I'll try to fix the occurrence in the course materials. I just want to use the same notation throughout the course. Then we will have a few examples now in order to determine, because there was a question here with polynomials, and we will look at them. In order for polynomials that describe running time, and describe this with the O notation. Concretely, the first example here is 5n to the 4 plus 3n cubed plus 2n squared plus 4n plus 1 is O of 4 of n, because this is the dominant part of this polynomial, and the constant also doesn't matter. You can simply do this by looking at it and say O of n to the 4, that's the order, the complexity of an algorithm that has that many primitive operations. You could also find an adequate C and N0, but this is something we are probably not doing very often anymore. And of course, we just look at the biggest term. There are a few exercises for you to try out now. I will also switch to the iPad in a moment and copy them, but I'm just leaving the slides here so you can see these examples, and you can try to to solve them or find their O complexity, and we'll be comparing them in a moment. I'll just leave the slides and copy this to my whiteboard. And so the first one is already solved. The next one is 5n squared plus 3n log n plus 2n plus 5. The third one is 20n cubed plus 10n log n plus 5. The fourth is 3 log n plus 2. The fifth one is 2 to the n plus 2 is something, and the sixth one is 2n plus 100 log n is. I'm switching now to the whiteboard briefly to show you them again. You can try to solve them, and we'll start discussing this momentarily. So I want to know from you for the number 2 here, 5n squared plus 3n log n plus 2n plus 5 is O of what? If you know it, send it to the chat or turn on your microphone. Waiting for your call to let us know what you think, of which order this is. It's O of n squared. Yes, that's correct, because this is the dominant term and the constants don't matter. O of n squared. Then the next one, 20n third, or n to the third, plus 10n log n plus 5 is O of what? N to the third. Yes, this is the dominant one. Then 3 log n plus 2 is O of what? O of log n. Again, we don't care about the basis, whatever. So if we wrote, I don't know, log 5, n, log 5 is also the constant. So it's just O of log n. Then we do the last one, the fifth we'll do at the end. So the last one is 2n plus 100 log n. It's O of what? It's O of n, yes, because these big constants here don't matter. It's just the dominant. And now we have 2 to the n plus 2. What O is that? O of what? So someone suggested it's O of 2 to the n plus 2. This is something we can actually simplify, and it's just O of 2 to the n, and I'll show you why. Because we have this term, which we called 2 to the n plus 2, and we can rewrite this as 2 to the n times 2 times 2. And then we just have this part as the constant, as the dominant part, and the constant is left out. So we just write this as O of 2 to the n. So this was our exercise here. And you should be all familiar with this O notation. We'll be looking at plenty of algorithms in this course in order to describe their complexity, but we're now moving there step by step. There are a few things you should pay attention at. If you have a statement or a term like 5n plus 3, you could say that this is O of n squared. Yes, this is correct, because n squared is an upper boundary of n. That's totally fine. But this does not provide you any useful insights. So your upper boundaries must be reasonable. And here writing O of n would be far more reasonable, because we will use these upper boundaries to describe complexity of algorithms. And if you pick an unnecessarily high complexity to describe this, it doesn't provide you any insights, because we're aiming for low complexity. So pick reasonable upper bounds. There are other things you could do, like you have 2n squared. You could say that this is O of 4n squared plus 6n log n. It's completely correct, but not fashionable. And always describe your function in simplest terms. Otherwise, you will just run into plenty of problems, and it again will not provide you with any reasonable insights. One thing you need to bear in mind is about constants and lower order terms matter. They eventually matter when you run your code, because if you have a big constant or a lot of lower order terms, they will still contribute to the execution time of your algorithm. We care about large n's in this course, and when you have large n's, your running time will be usually determined or largely influenced by this highest order term. But the lower order terms and the constants still matter. So it could happen if you have two algorithms that have a different complexity. Maybe the one with the higher complexity runs faster on very small inputs, because maybe you have an algorithm with a low complexity, say O of n, plus a huge constant, which is 1 million. And you have an algorithm which is n squared many primitive operations, then n squared will be less than n plus 1 million if your n is small. Once your n gets big, then n squared will dominate. But it could happen that eventually for small inputs, an algorithm with a higher complexity runs faster. But we care, first of all, in this course about algorithms and how to reduce their complexity. And typically, if you work well on reducing complexity of algorithms, they perform well on other inputs too, not just the worst case, but there could be exceptional situations where you get where this doesn't hold true, for example, for smaller inputs or some other strange and rare inputs. So we'll be seeing examples throughout this course. For example, when we look at sorting algorithms, there may be sorting algorithms for with very high complexity, but for some specific inputs, they may actually run faster than those low complexity sorting algorithms. But we aim for good complexity, and then typically they perform well in practice, but still maybe your customer requires you, yeah, I want to run this computation in a certain amount of time. And then maybe you still need to tweak your algorithm or put it in a profiler. But don't start working on the profiler first, because premature optimization is the root of all evil and will just get you into plenty of problems. But I've seen such cases too, where I worked in a team and the product manager said, yeah, I want to say this was a routing software. And the product manager said that a route of a certain distance within Germany needs to be calculated under certain settings in a certain amount of time, because this is what the customer expects. So you may get such a requirement on top, maybe rare, but could be, but still work in good complexity first, and this will save you lots of problems. Now we still have a little bit of time to look at another algorithm. And we will be calculating so-called prefix averages. And the prefix averages are something that looks a little bit cryptic to you, but I'll show you what it does. We have a sequence S, and the sequence S has integer or has indexes 0 up to j. So the indexes in this array, well, we go through from 0 to j, and j, it could be 0 up to n minus 1, because we have n many entries in S. So valid indexes are 0, 1, 2, 3, and so forth, up to n minus 1. And I'm summing together some of these indexes say from I to j, where j is initially 0, then 1, 2, 3, I'm summing these values in S together, and I divide them by j plus 1. And I store this in a sequence that I call A. These are so-called prefix averages, and because that equation or this term probably looks a little bit complex to you, we'll be actually just looking at an example, and we will see what this actually looks like on a real data set. So we have S, which are 1, 3, 2, and 5. And we'll be calculating the prefix averages in A. So I'm just writing down the equation here again. We say that A of j is divided by j plus 1. And we have a sum of index I of this, which is 0 up to j. And we take the index I. Now I want to know from you, maybe you can guess what's A of 0. If you have a clue what A of 0 could be, let me know in the chat and we'll compare. It's 1, which is correct because we're taking the 1, and this is the only one because j is also 0, so this is the only element we take, and we divide by j plus 1. J is 0, so we divide by 1. Then what is A of 1? I'll give you a moment to think about it and then share this in the chat. It's 2 because we are taking 1 and sum it with 3, so the first 2 elements in S, and we divide by j plus 1, so 1 plus 1, so it's 4 divided by 2, which is 2. Now we try A of 2 together. It's 1 plus 3 plus 2. So, and we divide by 2 plus 1. So we divide 6 divided by 3. It's also 2, and so forth. So this is the idea of the prefix averages. You can try this out for the last element yourself if you wish. And I now want to implement the prefix averages. And I will first of all propose an inefficient implementation. But I'm just doing what maybe the most easy way to implement this. So we say prefix average is 1 for a data set S. We want to know the length of S because we we just built this now in a very simple and primitive way, but I want to know what's the length of S. Then I need my data set A, where I put in the results. And if you ever see something like this in Python, that means I have a list where I have 0 elements in, and I multiply this with n, and that means I create a list that has n many elements, and they are all 0. So I'm just creating once this list where I put in my results. And then I go through my index j, and index j, we said j starts with 0, then 1, 2, 3, and so forth, up to n minus 1. This is what I can do with the range. I have a total variable, and then I go through all these elements from I up to j, but remember that Python range means the range excludes the last element. So it starts from 0 and goes up to the last element, where the last element is not included. So it goes from 0 up to j, because I put in j plus 1. And I'm adding to my sum the element I. And I just forgot the I here. So this is my inner index I. And I go through this. And then I'm updating A at position j. And I divide by j plus 1. Very important that you put the j plus 1 in a parenthesis. Otherwise, you're only dividing by j and you add 1 on top. And then we return A. And we can test this now. We can say our data is 1, 3, 2, and 5. And we call the prefix average is 1 on our data. And we get a 1, 2, 2, and the other element is the one we didn't calculate. It's 2.75. Do you think this is an efficient implementation? Maybe thumbs up, thumbs down. Thumbs up means efficient. Thumbs down, maybe improvable. So only negative responses. We can try to analyze it. We can say, so I can highlight this here in the shared screen. N is the length of S. This is a constant operation because the length is stored in a list. So I can just read it out. This is constant. How long does this one take? If you have a suggestion, how long does the second statement take? You can send this to the chat. So here I say this is O of 1. The next statement, I'm waiting for you. What do you think how long this takes? I don't get any responses, so I'm writing it's O of n because I'm creating a list with n many elements. So this cannot be done in a constant way. Now just adding some more spaces. We all have these complexities here. Then the outer loop is run. So this outer loop is run n many times because it's a range of here. The inner one is O of 1 because I'm just creating a sum that is 0. But remember, it will be run n many times. Then the inner loop is run j many times. But j also depends on n. Don't forget that because j depends on n, and then the inner loop is run j many times. This one here is the big question mark. We will see this in a moment. And this one here is also O of 1 because I'm calculating a sum and I'm storing it in A. But remember that single statement, or it's actually a few operations because I have a sum here, a division, I index, and I assign it. But this is still constant, but it's not just O of 1 because if I run it once, it's O of 1. But I run it again n many times. And the last one here is O of 1 because it's constant. So we got a student suggesting that the complexity is O of n squared. And this is correct. The big challenge is actually the statement where I've put this question mark here. And what we will see is we're wondering how often is this run in total. So and remember where I wrote here O of 1, this is just single time. Obviously will be run many times. Also here single time, but will be run n many times. Because that is a single statement, but will be run many times. And the inner one here will be run, but we can just write that this is actually n times, just to clarify this, because this comes n times. And in this inner loop, we actually see that this primitive operation is run in the inner loop. When the inner loop runs the first time, this is run once, because I depends on j plus 1, or j, but j depends on n, and n is initially 0, then 1, 2, 3, and so forth. So this statement in here is run in the first time the inner loop comes into play, it's run once. But then in the next iteration of the outer loop, the inner loop is run 2 times. When we run the outer loop the third time, the inner one is run 3 times, and so forth. So each time the inner loop or the outer loop has another iteration, the inner loop runs even longer, because it first runs once, the inner loop, then twice, then 3 times, 4 times, and so forth. And I need to sum all of this together, and I'll show you this in my slides. The problem is this line that has the index or line number 7, because there is this total that I'm creating, and that line is executed once, then 2 times, then 3 times, and so forth. And I need to sum all of this together to get the number of primitive operations that I'm spending on the inner loop. And the inner loop is actually the highest order term, because if I say, what is the sum 1, 2, 3, 4, 5, and so forth, if I sum this together, I can express this sum of I from I equals 1 to n as n times n plus 1 divided by 2. I can factor this out, so this would give me an n squared plus n divided by 2, but n squared plus n, I only care about the n squared in my O analysis, and divided by 2, I don't care about. So this is O of n squared. So line 7 is actually executed 1 plus 2 plus 3 plus whatever n many times. This takes O of n squared. And the other terms, we said, well, this is constant. This is O of n. This is constant, but run n many times, so O of n. Same for this one, a constant statement, run n many times, O of n, plus this one here, it's constant. What matters is this one. And this one here is executed O of n squared many times. So the only thing that matters is what happens in the inner loop, and that's why the running time of prefix averages 1 is O of n squared. There's a comment here. There's a statement you wrote in a comment. Let us know maybe what that means. And we have done this analysis, and in next week's lecture, we will try to make this faster. We still have a few minutes, so I will already do one attempt to do it faster with you, and we will see if this actually works, because we can do this in the remaining few minutes. Very easy. I can do one attempt to make it faster. The first part is the same. I can say, well, the second part is again the same. And eventually I need to return A, which is the same. And now I'm trying to build this with a loop as before. I say I have my loop for j in the range of n. And I want to update element j as a sum. So I want to sum everything from 0 up to j plus 1. This is a notation in Python that gives me a sublist. We'll see this in a moment, or a slice. I want to sum everything from index 0 up to j plus 1, but j plus 1 is something I'm excluding, and I divide this by j plus 1. So I'm using a native sum that is implemented in Python. Do you think this has a better complexity, yes or not? So green reaction means this has a better complexity, or red means worse complexity, because I've just eliminated a loop and I'm using this native function in Python. So we got one student who thinks it's faster. What do the others think? Do they think it, or maybe faster in terms of their running time? Does it give me a better complexity? And there are students disagreeing. It does not give me a better complexity because I'm using the sum function, but internally it's also represented with a loop. And just to show you what this notation here means is, if I take my data and I say I want everything from index 0 up to 2, for example, what it gives me is a slice. It gives me everything from 0 and 1, but 2 is an upper index that is excluded. I could also put in a 3, then I get a slice of my data. If you have a 0, you can also just leave it aside, and then the 0 is put in implicitly, but prefix averages 2 will not have a better complexity, because in here, eventually, in this inner loop, I still need to go through all these entries as before. The inner loop, you don't see it, but that's what eventually the sum function is doing it. So it may run a little bit faster if you measure running time, because you're using an internal function in Python that is maybe taking advantage of some tricks on your computer, but it will not give me a better complexity because this part still uses O of j plus 1 time. I'll show you this in the slide, and then we're also done very soon. So this is the prefix averages 2 we have just implemented, and line 5 is now a function call, but the function call still takes O of j plus 1 time. And I'm running this n many times because I have the outer loop. So eventually, building the sum still takes 1 plus 3 plus 3, 4, and so forth primitive operations, and is therefore still O of n squared in total. Next week in the lecture, we will try to do this faster or with a better complexity. There are already some initial assignments for complexity analysis that you can also do. I know it was a double lecture today, but you also have some time for revision. And next week, if you have any questions, come also to the lab sessions, because the lab sessions are meant for you to work on the coursework, but I'm also happy to help with any questions you may have or revision you need from the lecture. And next week in the lecture, which is after the lab sessions, we will try to improve this algorithm in terms of its running time complexity. I wish you a good weekend and see you next week. If you have any questions until next week, Friday, also send an email or something. I'll be happy to help. Otherwise, I hope to see many of you in the lab. Take care. Bye-bye.